Before we begin, let me ask you something. When you drop a stone and watch it fall, what unseen command draws it downward with absolute certainty? If the space around you could whisper its secrets, would it reveal that every motion you take for granted is shaped by a silent structure you cannot touch? And if the universe has been following the same quiet rule since the first stars ignited, why has it taken us so long to understand the force that threads everything together? These questions linger at the edge of ordinary experience, inviting us to look beyond what our senses can show and into the deep framework of reality itself. For most of human history, people tried to understand falling objects using nothing more than everyday intuition. Aristotle believed that objects moved toward their natural place, a simple idea that seemed reasonable because stones fell and flames rose. But even though his reasoning guided scholars for centuries, it was based on observation without measurement, a world interpreted through appearances rather than experiments. This approach served as a foundation, but could not reveal the precise behavior that gravity imprints on every object in motion. The turning point arrived many centuries later when Galileo began timing falling bodies on inclined planes, discovering that they accelerated at a constant rate. With careful repetition, he challenged the belief that heavier objects fall faster and replaced older assumptions with quantitative evidence. His simple ramps, wooden balls, and water clocks became tools that would reshape physics, showing that the universe responds to measurable laws rather than philosophical expectations. Galileo's insights set the stage for a revolution that unfolded in the 17th century when Isaac Newton saw farther by, combining mathematics with observation. Newton recognized that the same rule guiding a falling apple could also guide the motion of the moon. By proposing the law of universal gravitation, he connected terrestrial and celestial behavior with a single mathematical expression. Gravity, in Newton's view, acted instantly across space, pulling masses toward one another with a strength proportional to their mass and weakened by distance. This description matched observations of planetary orbits with extraordinary precision. It allowed astronomers to predict the paths of comets and the timing of tides. It was so accurate that in the 19th century, astronomers noticed a small irregularity in the orbit of Uranus. Instead of assuming Newton was wrong, they wondered whether another unseen planet might be tugging on it. Using Newton's equations, they calculated where the hidden body should be. When telescopes finally turned to that point in the sky, they found Neptune almost exactly where the numbers predicted. This remains one of the most celebrated successes of Newtonian mechanics, a demonstration of how a well-tested theory can reveal something never before observed. Yet, even with such triumphs, Newton's theory left an unresolved question that would linger for centuries. He could describe how gravity acted, but not what caused it. He wrote that he did not invent hypotheses, leaving the mechanism behind gravity an open problem. Why should masses attract one another across empty space? How could a force reach across the void without a physical medium? These puzzles troubled many thinkers, including Newton himself. Meanwhile, advances in measurement uncovered slight discrepancies in planetary motion, most notably the precession of Mercury's orbit. Though small, these differences signaled that Newton's theory, for all its power, might not be the final word. As the 19th century ended, physicists searched for deeper explanations. They refined astronomical data, catalogued orbital variations with growing precision, and tested the behavior of falling objects in every context available. They expected that a hidden factor or unseen mass would eventually account for every mismatch. But instead, the evidence hinted at something more profound, something beyond the reach of Newton's concepts. The natural world was whispering again, just as it had for Galileo and Newton, signaling that another shift in understanding was approaching. The stage was being set for a new vision, one in which gravity would no longer be seen as a force that acted at a distance, but as a feature woven into the geometry of space and time. The search for clarity in the behavior of gravity continued as the 19th century gave way to the 20th. Astronomers kept gathering data, refining measurements of planetary orbits until even the smallest deviations became impossible to ignore. Among these stood the motion of Mercury, whose closest point to the Sun drifted slightly more than Newtonian predictions allowed. The difference was tiny, only a few arc-seconds each century, yet it persisted even after every plausible source of error had been removed. Physicists tried adjusting the distribution of mass in the solar system, or imagining a small unseen planet orbiting near the Sun. Nothing solved the issue with the precision demanded by observation. It was as though nature was leaving a faint signature that the rules familiar to Newton were not the deepest rules governing reality. While these puzzles accumulated, Albert Einstein was rethinking motion itself. His work on special relativity had already changed the understanding of time and space, showing they were not separate entities, but intertwined aspects of a single fabric. This fabric shaped how objects moved, how clocks ticked, and how rulers measured distance. Yet special relativity did not include gravity, and Einstein began to suspect that the key lay in the way acceleration mimicked the experience of gravitational pull. If someone in a sealed room felt pressed against the floor, could they determine whether they were standing on a planet or accelerating through empty space? Einstein realized they could not. This idea, called the equivalence principle, became the cornerstone of his search for a new description of gravity. Instead of treating gravity as an invisible force acting between distant bodies, Einstein imagined that massive objects changed the geometry of space and time itself. In this picture, planets follow the straightest possible paths through a curved landscape created by the presence of stars and planets. The concept was difficult to visualize, since human senses do not reveal the shape of space-time, but the mathematics that Einstein crafted captured this curvature with extraordinary precision. His field equations, completed in 1915, link the distribution of mass and energy to the curvature of space-time, producing a theory capable of explaining the motion of Mercury and the behavior of light near massive bodies. When Einstein applied his equations to the solar system, the precession of Mercury's orbit emerged with exact agreement to observed values. No hidden planet was needed, no patch or correction. For the first time, the small drift in Mercury's path made perfect sense. Einstein had not just improved Newton's theory. He had replaced it with a deeper framework, one in which gravity was no longer an instantaneous pull across distance, but a manifestation of geometry itself. Light rays bent when passing near the Sun, not because light had weight, but because space and time around the Sun were curved, guiding light along a different path. Clocks ticked at different rates in strong gravitational fields, not because they malfunctioned, but because time itself changed, depending on the curvature present. Although the mathematics of general relativity was challenging, the predictions were clear enough to test. Einstein proposed that during a total solar eclipse, stars near the Sun's edge would appear slightly shifted because their light would curve on its way to Earth. In 1919, an expedition led by Arthur Eddington traveled to observe this effect. Despite difficult weather and equipment limitations, the measurements they obtained supported Einstein's predictions. Newspapers across the world announced that Newton's laws had been surpassed and that the understanding of gravity had entered a new era. The universe had revealed another layer of its structure, one that had remained hidden until Einstein found the language to describe it. Yet even as general relativity triumphed, a quiet mystery deepened in the background. If gravity was truly geometry, what exactly shaped that geometry at the smallest scales? Space and time, smooth in Einstein's equations, seemed at odds with the quantum world, where energy came in discrete amounts and uncertainty defined the limits of knowledge. The same universe that curved under the weight of stars also danced in probabilistic patterns in the realm of atoms. The two descriptions worked flawlessly in their own domains, but they did not blend together. Beneath the elegance of relativity and the precision of quantum theory, another unknown waited. The questions raised by this tension between the smooth geometry of relativity and the granular nature of quantum physics would not be resolved quickly. But long before scientists turned their attention fully to that frontier, general relativity itself began to uncover new features of gravity that no earlier theory had predicted. One of the most surprising came from examining how mass shapes the path of not only planets and light, but even the flow of time. Experiments using delicate atomic clocks showed that time passes slightly more slowly near the surface of Earth compared to clocks placed at higher altitudes. This difference is tiny but measurable, and it arises directly from the curvature described by Einstein's equations. The closer a clock is to a massive object, the more space-time is warped, and the more slowly time unfolds. What once seemed like a philosophical idea became an experimentally verified aspect of reality. As technology advanced, these relativistic effects became vital for systems that depend on precise timing. Satellites orbiting Earth carry clocks that tick more quickly than those on the ground because they experience weaker gravity. Without adjusting for this difference, navigation signals would drift, and global positioning systems would fail within minutes. The clocks were not broken. They were faithfully following the rules woven into space-time. It was a quiet confirmation that Einstein's vision, though radical in its time, had become part of the machinery of everyday life, guiding airplanes, ships, and the phones in our pockets. Yet the true depth of general relativity appeared most vividly when scientists studied objects so massive that they reshaped space-time in extreme ways. Einstein himself found that his equations allowed solutions where curvature tightened without limit, forming regions from which nothing could escape. Though he doubted that nature would permit such extremes, later researchers took the mathematics seriously and explored its implications. Gradually, these solutions became known as black holes, places where gravity grew so intense that escape was impossible. At first, these ideas were treated as mathematical curiosities, not as physical possibilities, but the more astronomers observed the sky, the harder it became to ignore signs of immense unseen masses. Binary star systems displayed motions indicating that one member was compact and extraordinarily heavy. Vast amounts of energy were emitted from regions where gas spiraled toward an invisible center. Jets of charged particles streamed across space from the hearts of distant galaxies, powered by processes that required immense gravitational energy. Each piece of evidence pointed toward objects that matched the properties predicted by general relativity. Einstein's equations, written to explain the orbit of Mercury and the bending of starlight, now described engines that shaped entire galaxies. Even so, the rise of black hole astronomy did not settle every question. Instead, it sharpened the boundary between what was known and what remained mysterious. Inside a black hole, space-time curvature grows beyond the reach of current theory, and the behavior predicted in that region indicates that our understanding is incomplete. The singularity predicted by relativity is not a physical place, but a sign that the mathematics breaks down. It tells us that a deeper description of gravity is needed, one that can handle situations where quantum behavior and curvature become equally important. This remains one of the largest puzzles in modern physics, a frontier where observation and theory must eventually meet. The journey from Aristotle's explanations to the modern picture of curved spacetime shows how each era uncovered a deeper layer of truth. The falling stone that once seemed so simple now hints at a universe shaped by geometry, time dilation, and extreme objects hidden behind horizons. Gravity has revealed itself through careful observation, measurement, and reasoning across centuries, guiding scientists toward an ever richer understanding. And yet the force that shaped the first stars and governs the motion of entire galaxies still keeps its ultimate nature concealed. The story of gravity has moved from ancient philosophy through Newton's equations to Einstein's curved universe, but it has not ended. It continues to evolve with every new measurement and every new question, inviting us to look again at the familiar pull we feel every moment and wonder what deeper structure lies beneath it. Before we step deeper into the story of gravity, consider a simple question that unsettled even the greatest thinkers. If you were sealed inside a quiet room with no windows, and suddenly you felt yourself pressed against the floor, how would you know whether you were standing on a planet or riding inside a rocket accelerating through the emptiness of space? If these two experiences feel identical, what does that say about the nature of gravity itself? And if the universe can disguise motion as weight, what other secrets might be hidden behind sensations we accept as ordinary? Einstein began with these questions, not with complicated machinery or distant stars, but with the feeling of weight itself. He imagined a person falling freely toward Earth. In that moment of descent, the person would feel weightless because both their body and whatever they carried would accelerate together. This simple thought revealed that gravity and acceleration share a deep connection, one that no earlier theory had fully explored. Einstein called this insight the equivalence principle, and it became the seed from which his entire revolution grew. It led him to wonder whether gravity was not a force, but something more subtle, something built into the fabric of reality. As he worked through these ideas, Einstein realized that the classical picture of space and time could no longer hold. Special relativity had already shown that the speed of light remained constant for all observers, and that space and time were intertwined in ways that defied everyday intuition. If these principles were true, then gravity could not be an invisible pull acting across distance. Instead, Einstein proposed that mass and energy shape the structure of space-time itself, bending it in ways that guide the motion of planets, light, and even time. To describe this geometry, he began crafting a set of equations that linked matter to curvature, equations that would become the foundation of general relativity. These equations did not emerge quickly. Einstein spent years refining them, checking whether they could describe the known behavior of planets and light. Finally, in 1915, he presented the completed field equations to the Prussian Academy of Sciences. The mathematical language was intricate, yet its meaning was profound. The equations declared that matter tells space-time how to curve, and that curved space-time tells matter how to move. This replaced the idea of gravity as a pull and revealed it instead as a feature of geometry. Planets follow curved paths, not because something pulls them, but because they travel along the straightest possible routes in a warped landscape. One of the first tests of the new theory came from the long-standing puzzle of Mercury's orbit. Astronomers had known for decades that Mercury's elliptical path rotated slightly more than Newtonian predictions allowed. The discrepancy was small but persistent, surviving every attempt to adjust the calculations. When Einstein applied his new equations, the difference emerged naturally and matched the observed value with perfect agreement. This success gave Einstein confidence that he had uncovered a deeper truth, one capable of explaining phenomena that had puzzled scientists for more than a generation. But general relativity offered more than answers to old questions. It predicted entirely new effects that no earlier theory had imagined. Light would bend when passing near a massive body, because mass curves space-time. Time would slow down in stronger gravitational fields, because the flow of time itself depends on the structure of space-time. Even empty space around a spinning object would twist slightly, carrying nearby objects with it. These were not mathematical curiosities, but physical predictions awaiting confirmation. The first major test came in 1919 during a total solar eclipse. Light from stars passing close to the sun would bend on its journey to Earth. Eddington's expedition set out to measure this shift using delicate photographic plates. Despite clouds and technical challenges, the data showed a deflection matching Einstein's prediction. Newspapers around the world heralded the result as a triumph of human understanding. The familiar image of a universe governed by invisible forces gave way to a deeper vision, one in which geometry itself shaped reality. This new theory did more than rewrite textbooks. It changed the way scientists thought about the universe. If gravity was curvature, then the fabric of space-time could behave in ways that no earlier idea allowed. It could stretch, ripple, and respond to the presence of mass. It could form regions where time slowed dramatically or where light could not escape. These possibilities were not speculation, but direct consequences of Einstein's equations, consequences that scientists would explore throughout the 20th century and beyond. Einstein's new vision of gravity began reshaping scientific thought almost immediately, yet many of its implications emerged slowly as researchers explored the mathematics more deeply. One of the earliest realizations was that spacetime could not be treated as a passive stage. It was dynamic, responding to matter and energy in ways that created phenomena no classical framework could anticipate. The bending of starlight near the sun was only the beginning. If mass could curve spacetime, then the motion of planets, the flow of time, and even the path of light itself were all consequences of geometry. This idea seemed abstract at first, but as scientists worked through detailed calculations, they found that the equations predicted behaviors that could be tested with remarkable precision. Time dilation was among these surprises. Einstein showed that clocks run more slowly in stronger gravitational fields. The effect is subtle when comparing two clocks on Earth at different heights, yet modern atomic clocks can measure differences that arise over only a few meters. These experiments confirmed that time itself is not absolute. It stretches and compresses depending on where one stands in the curved landscape of spacetime. Planetary motion, once viewed through Newton's lens of invisible forces, now appeared as a natural result of objects following the most direct possible paths through warped geometry. Light, the fastest thing in the universe, could no longer be thought of as moving through a rigid background. Its trajectory bent whenever it crossed regions shaped by mass or energy. As physicists explored further, they discovered that the new theory did not simply refine Newtonian predictions. It opened doors to entirely new realms of understanding. The equations suggested that spacetime could ripple when massive objects accelerated, creating disturbances that traveled outward at the speed of light. These ripples, called gravitational waves, were predicted long before instruments existed to detect them. Einstein himself suspected they might be forever beyond experimental reach because the distortions they produced were unimaginably small. Yet the theory insisted that if two massive bodies spiraled around one another, spacetime would quiver like the surface of a pond struck by a pebble. This idea remained a theoretical curiosity for decades, but it hinted at a universe filled with silent vibrations waiting to be heard. Another striking implication emerged when researchers studied solutions to the field equations that described extremely compact masses. Under certain conditions, space-time curvature tightened so dramatically that it formed a region from which nothing, not even light, could escape. These solutions hinted at black holes, though the term itself had not yet been coined. At first, many dismissed these predictions as mathematical artifacts, arguing that nature would not permit such extreme objects to form. But as telescopes improved and astronomers observed stars moving in peculiar ways, the possibility that such objects were real became increasingly difficult to ignore. The theory that began as an explanation for Mercury's orbit now pointed toward entities far more exotic than anything classical physics allowed. General relativity also predicted that rotating bodies would drag spacetime along with them, producing an effect known as frame dragging. This twisting of spacetime is minuscule near Earth, but it becomes significant around rapidly spinning stars or the central regions of galaxies. The concept challenged intuition, suggesting that space itself could swirl like a fluid in the presence of rotation. Experiments in the late 20th and early 21st centuries confirmed the effect, showing that Einstein's equations remained accurate even in subtle situations where classical theories offered no guidance. Despite these predictions and confirmations, the new picture of gravity raised questions as quickly as it solved them. If spacetime could stretch and ripple, what determined its ultimate shape? If massive objects could curve spacetime so strongly that they created horizons, what happened inside regions where the curvature grew without limit? If time slowed in strong fields, How did this affect the evolution of stars and the behavior of light in distant galaxies? Each answer widened the horizon of inquiry, demonstrating that the geometry of space-time was more complex and more dynamic than anyone had imagined a century earlier. As the implications of general relativity spread through the scientific community, it became clear that Einstein had not merely replaced Newton's equations. He had redefined the foundation on which all future physics would stand. Gravity was no longer a mysterious pull reaching across empty space. It had become a manifestation of structure, a clue pointing toward the deeper architecture of the cosmos. Yet even with this breakthrough, a quiet tension remained. The quantum world, with its discrete energy levels and inherent uncertainty, did not easily fit into a theory built on smooth geometry. Somewhere in this mismatch lay the next frontier, hinting that the revolution Einstein began was not complete, but only entering its next chapter. Einstein understood that a theory as bold as general relativity would rise or fall on its ability to withstand experimental scrutiny. The bending of starlight had provided a dramatic first confirmation, but this was only one test among many that would eventually shape the theory's legacy. As researchers examined its predictions more closely, they discovered that general relativity intertwined with the real world in ways both subtle and unavoidable. Every precise measurement of gravity, every observation of planetary motion, and every experiment involving the passage of time became an opportunity either to strengthen or to challenge Einstein's vision. Instead of a fragile idea struggling to survive, general relativity proved remarkably resilient. Far from breaking under pressure, it grew more firmly rooted with each new attempt to test it. One area where the theory quickly demonstrated its power was in explaining how light behaves in a gravitational field. Einstein showed that light loses energy as it climbs out of a gravitational well, lowering its frequency in a phenomenon known as gravitational redshift. This prediction was tested in the 20th century when researchers compared the frequencies of gamma rays emitted at different heights in Earth's gravitational field. The results agreed precisely with the values demanded by the theory. These experiments were not merely technical achievements. They revealed that gravity influences even massless particles, shaping the trajectory and energy of light through curvature rather than force. Such findings deepened the sense that Einstein had uncovered a fundamental truth about the structure of nature. Another striking confirmation came from binary star systems, pairs of stars orbiting around a common center of mass. When one member of such a system emits regular pulses of electromagnetic radiation, astronomers can monitor the timing of those pulses with extraordinary precision. A famous binary pulsar discovered in the 1970s allowed scientists to observe how the orbit shrank over time. According to general relativity, the system should emit gravitational waves, slowly carrying away energy. The observed decrease in orbital period matched Einstein's prediction so closely that it became one of the strongest indirect confirmations of gravitational radiation long before direct detectors existed. The universe itself was acting as a laboratory, demonstrating that the geometry of space-time could radiate energy across cosmic distances. As observational tools grew more sophisticated, general relativity also found relevance in everyday technologies. Satellite-based navigation systems rely on synchronized clocks placed in orbit around Earth. These clocks tick at different rates compared to clocks on the ground because they experience weaker gravity and move at high velocities. Engineers must incorporate both special and general relativistic corrections to keep positioning accurate. Without these adjustments, the system would drift rapidly and become useless. This practical requirement showed that relativity was not an abstract theory reserved for extreme situations. It had become an essential component of the digital infrastructure guiding modern transportation and communication. Still, the most dramatic implications of general relativity emerged when scientists examined environments where curvature reaches its highest levels. Massive stars collapsing under their own gravity form regions with intense warping of space-time. The equations reveal that under certain conditions, no known force can halt the collapse. The resulting object, a black hole, possesses an event horizon beyond which information cannot return. Although Einstein doubted such objects would form naturally, observations in the late 20th and early 21st centuries confirmed that they are indeed part of the universe. Stars near the center of the Milky Way orbit a dark mass whose gravitational influence betrays its presence. Gas falling toward compact objects emits radiation characteristic of spiraling material nearing an event horizon. These signatures align with the predictions of general relativity and leave little doubt that black holes are not mere mathematical curiosities but genuine features of the cosmos. Yet even as the theory continues to succeed, it does not resolve every mystery. The nature of space-time at extremely small scales remains unknown. The behavior of singularities, places where curvature grows without bound, marks the breakdown of the theory's applicability. The quantum world resists being folded into a geometric description, raising questions about how space, time, and gravity behave when energies climb high enough for both quantum effects and curvature to become equally important. Einstein's revolution reshaped physics, but it left behind a frontier he could not cross. Still, the theory's achievements cannot be overstated. It transformed the understanding of movement, energy, and time. It explained puzzles that had lingered for centuries. It revealed structures in the universe that no earlier theorist had imagined. And it continues to guide exploration today as astronomers study extreme environments throughout the cosmos. General relativity does not merely describe gravity. It offers a glimpse into the deep architecture of the universe, a framework that has withstood every test placed before it, while still leaving room for discoveries yet to come. Before we move forward, let us pause with a question that hides in the starlight overhead. If the fabric of space-time truly bends and stretches, then every beam of light crossing the universe carries a record of that shape. What would we learn if we could read those silent distortions? Could the stars themselves reveal the invisible contours of gravity, showing us whether Einstein's vision matches reality, or whether the cosmos contains surprises still concealed behind the glow of distant suns? The story of testing general relativity begins with the simplest of tools, not with advanced satellites or massive observatories, but with careful observation and precise comparison. Einstein's equations predicted that light would bend as it traveled near a massive object, not because light possessed weight, but because it followed the curvature of space-time. This prediction became the focus of one of the most famous experiments in the history of science. During a total solar eclipse in 1919, when the moon blocked the bright glare of the sun, the faint stars near the sun's edge became visible. If their apparent positions shifted outward, it would show that their light had curved on its journey to Earth. Eddington's expedition, working under difficult conditions, captured photographic plates that revealed exactly this effect. The measured deflection agreed with Einstein's prediction, marking the first major observational triumph of general relativity and signaling to the world that the theory had entered not just mathematics, but measurable reality. Yet this was only the beginning. Another key test came from a phenomenon predicted by relativity known as gravitational redshift. If light climbs out of a gravitational well, its frequency must decrease. This effect is not visible to the eye, but with sensitive instruments, it can be measured. In the 1950s, Pound and Rebka conducted an experiment using gamma rays sent between different heights in a Harvard physics building. They observed the shift exactly as Einstein's theory required. In this demonstration, gravity revealed that it influences not just the motion of planets or falling objects, but the very energy of photons. These findings helped establish that general relativity was not a theory confined to distant stars. It affected the behavior of light here on Earth, in controlled experiments that anyone could verify. As the 20th century progressed, clocks grew more precise, and relativity found another arena in which to prove itself. According to the theory, time flows differently depending on gravitational strength and velocity. Clocks placed on airplanes tick at rates that differ from clocks kept on the ground. When researchers compared them after long flights, The differences match the predictions of relativity with remarkable accuracy. These experiments confirmed that time dilation is not a theoretical construct, but a physical behavior of reality. Without correcting for these effects, global navigation systems would accumulate large errors. The satellites orbiting Earth move quickly and experience weaker gravity, making their clocks run slightly faster than those on the surface. Engineers adjust for this difference because the machinery of relativity has become part of the everyday world, shaping the accuracy of systems that guide travel and communication. Other predictions required even more sensitive instruments. General relativity suggested that massive rotating bodies would pull space-time around with them, an effect known as frame dragging. Detecting this required a satellite equipped with gyroscopes of extraordinary precision. Gravity Probe B, launched in the early 21st century, observed the minute twisting of space-time caused by Earth's rotation. Though the effect was extremely small, the results matched Einstein's equations, confirming another subtle prediction that would have been inconceivable under Newtonian gravity. The universe itself provided additional tests in the form of gravitational lensing. When light from distant galaxies passes near a massive cluster, the curvature of spacetime bends it, creating arcs, rings, or even multiple images of the same object. These distorted shapes appear regularly in deep sky photographs and have become a vital tool for mapping the distribution of mass in the cosmos. One of the most striking examples is the Bullet Cluster, where observations of gravitational lensing revealed that most of the mass resides not in the glowing gas, but in something invisible. This evidence supports the existence of dark matter and showcases gravity as a guide to otherwise hidden structures. Beyond these phenomena lies a final realm where general relativity showed its strength long before direct detection became possible. The study of the Hulse-Taylor binary pulsar revealed that its orbit shrank over time at a rate consistent with the emission of gravitational waves. Though the waves themselves had not yet been observed, the behavior of the system aligned so precisely with predictions that the discovery earned a Nobel Prize. It was as if the universe had whispered its confirmation through rhythmic pulses across space. The accumulation of evidence supporting general relativity grew steadily as astronomers refined their instruments and pushed their observations deeper into the sky. Each new generation of technology allowed them to test the theory in environments more extreme than the last. What began with the bending of starlight during an eclipse expanded into a full exploration of the cosmic landscape, revealing behaviors of gravity that no earlier era could have imagined. The universe became not only a backdrop for Einstein's ideas, but a vast laboratory where the laws of space-time revealed themselves with increasing clarity. One of the most visually striking confirmations of general relativity appears in the form of Einstein rings. When a distant galaxy aligns, precisely behind a large mass, such as a galaxy cluster, its light spreads into a circular arc as it passes through curved space-time. These rings are not mere illusions produced by faulty lenses. They are the natural signature of light traveling along the shape carved by gravity. Each ring tells a story about the distribution of mass in the foreground object, including the presence of matter that does not emit light. Astronomers can measure the thickness, brightness, and symmetry of these arcs to reconstruct the invisible architecture of the cosmos. In doing so, they confirm yet again that Einstein's framework describes the path of light across billions of years. Another realm where general relativity shines is the study of compact stars. Neutron stars, the dense remnants of collapsed massive stars, provide natural laboratories where gravity reaches intensities far beyond anything possible on Earth. These stars pack more mass than the Sun into a sphere scarcely larger than a city. Their rapid rotations and strong magnetic fields produce pulses of radiation that sweep across Earth at regular intervals. By measuring these pulses with extreme precision, astronomers can track how the orbits of binary neutron stars evolve over time. In every case where such systems have been studied, the observed rate of orbital decay matches the predictions of energy lost through gravitational wave emission. Even before detectors on Earth could listen for these waves directly, the behavior of distant stars confirmed their existence. The deflection of light and the timing of pulsars reveal how spacetime behaves in extreme conditions, but the effects of relativity also appear quietly in the motions of stars near the center of the Milky Way. Over decades, astronomers have tracked a group of stars orbiting an unseen mass at the heart of our galaxy. Their paths curve so sharply and their speeds rise so high that no ordinary object could account for the gravitational pull. The only explanation consistent with all observations is a supermassive black hole. General relativity predicts exactly how such a massive body would influence nearby stars, and the match between theory and measurement is extraordinary. The observed orbits trace out the unseen shape of spacetime, revealing both the presence and the mass of the central object with remarkable fidelity. Even beyond these dramatic confirmations, relativity appears in subtler places. The way galaxies rotate, the distribution of mass in clusters, and the movement of distant supernovae all contribute to a portrait of a universe shaped by gravity on the largest scales. Observations from spacecraft and ground-based telescopes show that the cosmic microwave background, the faint afterglow of the early universe, carries patterns that reflect the influence of gravity over billions of years. These patterns align with general relativistic models of how matter clustered in the young universe, forming the seeds that later grew into galaxies and clusters. The match between theory and observation is not one coincidence, but a tapestry of evidence woven across multiple independent lines of inquiry. Yet even with so much verification, general relativity remains a theory that invites deeper questioning. Each experiment confirms its predictions, but each confirmation also draws attention to phenomena that lie beyond its reach. The behavior of the universe on the largest scales suggests the presence of dark energy, a component that influences the expansion of space and yet remains poorly understood. The way galaxies move indicates the presence of dark matter, which cannot be explained by ordinary particles alone. These discoveries do not contradict Einstein's theory. Instead, they show that gravity operates within a cosmos whose full contents are not yet known. General relativity describes how matter shapes space-time, but it cannot reveal the true nature of the unseen matter and energy that dominate the universe. The success of relativity across such a wide range of tests has created an unusual situation in modern physics. On the one hand, the theory has passed every challenge with extraordinary precision. On the other hand, it leaves fundamental questions open. How does gravity behave at extremely small scales where quantum effects become important? What happens in regions where curvature grows without limit? How do we understand the interior of a black hole or the earliest moments of the universe? Moments when space-time itself was compressed into densities beyond current theory. These are not flaws in Einstein's vision, but invitations to expand it. Still, the evidence gathered from the sky forms a powerful narrative. From bending starlight to shrinking orbits, from distorted galaxies to spinning stars, the universe confirms repeatedly that gravity is not a force acting across distance, but the shape of space-time itself. Every measurement tightens the frame of understanding and deepens the mystery of what lies beyond its edges. The sky has become a canvas on which the geometry of the cosmos is drawn in light, motion, and time, revealing a structure that continues to challenge imagination while grounding itself firmly in observation. The sky continued to reveal its evidence as new instruments reached levels of sensitivity once thought impossible. With each improvement, general relativity encountered yet another opportunity to fail, yet it did not. Instead, the universe answered Einstein's predictions with a consistency that strengthened the theory at every turn. Even so, the most profound test of all remained out of reach for nearly a century. Einstein had predicted that when massive objects spiral together, the curvature of space-time itself should tremble, sending waves outward at the speed of light. These gravitational waves would stretch and compress space by amounts so small that detecting them seemed far beyond the capability of human engineering. For decades, the idea existed only on paper, a beautiful mathematical consequence with no direct experimental confirmation. But the universe had been generating these waves since its earliest moments, waiting only for instruments capable of hearing them. That moment arrived in the early 21st century, with the development of laser-based observatories designed to measure distances with unimaginable precision. These detectors used beams of light reflected across long tunnels to sense distortions in space-time far smaller than the width of a proton. The challenge was immense. Every vibration, every sound, every subtle motion of Earth itself had to be isolated or filtered away. The detectors waited silently for a signal, listening to the universe with patience that mirrored the long history of relativity itself. Then, in the year 2015, a faint signature appeared. Two distant black holes had spiraled into one another, merging in a burst of gravitational energy that rippled across the cosmos. By the time those waves reached Earth, they carried only a whisper of their original strength, yet the instruments captured them with clarity. The signal matched the waveform predicted by general relativity, revealing the masses and final merger of the black holes with remarkable detail. It was the first direct detection of gravitational waves, a milestone that confirmed one of Einstein's boldest predictions and opened a new era in astronomy. The discovery did not stand alone. More signals followed, each produced by cosmic events so distant that their light had barely begun its journey when life first emerged on Earth. The data revealed collisions between black holes and even the merger of two neutron stars, an event that produced both gravitational waves and electromagnetic radiation. This combination allowed astronomers to compare two ways of observing the same cosmic cataclysm. The agreement between these observations and the predictions of relativity strengthened confidence in the theory, while providing new information about the nature of dense matter and the behavior of gravity under extreme conditions. For the first time, scientists could listen to space-time itself, hearing the universe through vibrations rather than light. The successes did not end there. Around the same time, a global network of radio telescopes joined forces to create an instrument capable of imaging the region near a black hole's event horizon. By combining signals gathered from locations scattered across Earth, researchers formed an observatory with the effective size of the planet itself. This method, known as very long baseline interferometry, allowed them to resolve details smaller than the shadow cast by a black hole on the surrounding glow of heated gas. In the year 2019, the collaboration released the first image of the supermassive black hole in the center of the galaxy, called M87. The dark, circular region, surrounded by a ring of glowing material, aligned closely with the silhouette predicted by Einstein's equations. It provided visual confirmation that the curvature near a black hole behaves exactly as general relativity describes. Later, work produced an image of the supermassive black hole at the center of the Milky Way, offering yet another test of the theory in a very different environment. These achievements demonstrated that general relativity had reached a level of verification unmatched by almost any other physical theory. It had succeeded under conditions ranging from the quiet drift of clocks in Earth's gravity to the violent merger of black holes billions of light years away. Yet despite this success, the theory continued to point toward mysteries it could not solve. It described how gravity behaves across the cosmos, but offered little insight into the nature of the dark matter whose gravitational effects shape galaxies. It explained the cosmic expansion, but could not reveal the true nature of dark energy that accelerates that expansion. It predicted singularities inside black holes, but acknowledged that these singularities signaled the breakdown of the theory itself. In other words, the evidence supporting general relativity was vast, yet it illuminated the boundaries of the theory as clearly as its strengths. Through each of these experiments, the sky has acted as both witness and teacher. Every beam of light bent by a galaxy cluster, every pulse from a spinning neutron star, every ripple in spacetime captured by sensitive detectors, has offered another line of evidence that gravity is geometry. The universe itself has become the final judge of Einstein's ideas, presenting case after case in a courtroom of stars and galaxies. The verdict remains consistent. The theory holds. The predictions match. Reality bends as Einstein saw it. But the great success of general relativity does not diminish the sense of mystery. Instead, it deepens it. Because if a theory so precise and so thoroughly confirmed still points toward limits, then the next chapter of gravity's story lies somewhere beyond those limits, waiting for the tools and insights that will carry physics further still. The evidence in the sky confirms what we know. It also reminds us how much remains hidden in the vast architecture that shapes the universe. Before we follow gravity into the hearts of stars, consider one more question that hides behind every point of light in the night sky. If a star spends its entire life fighting a quiet battle between outward fire and inward pull, what happens when that balance falters? What secret negotiations unfold within a sphere of gas so hot that atoms break apart, yet so delicate that a slight change in pressure can seal its fate for billions of years? And if the stars themselves are shaped entirely by the same gravity that guides falling apples and orbiting planets, what deeper story does each shining point reveal about the force that governs the universe? Every star begins its existence inside a cloud of gas and dust drifting through the galaxy. These clouds are vast, stretching across many light years, yet they are cold and thin enough that their motions seem almost frozen over human timescales. But gravity never rests. Over long periods, small regions within these clouds become slightly denser than their surroundings. As gravity strengthens in these pockets, the gas begins to collapse inward. Once the collapse starts, it feeds upon itself, drawing in more material and heating up the forming core. This is the moment when gravity first asserts its role in building a star. Without it, the gas would never gather tightly enough to ignite nuclear fusion, the process that defines a star's life. As the forming star contracts, its central temperature rises. Hydrogen atoms collide with such force that they merge into helium, releasing energy. This release of energy creates an outward pressure that pushes against gravity. The star settles into what astronomers call hydrostatic equilibrium, a delicate balance between the inward pull of gravity and the outward pressure of fusion. During this stage, which lasts for most of a star's lifetime, the star shines with steady light, maintaining a stable structure as long as hydrogen remains abundant in its core. The same gravity that once pulled the cloud together now acts as a boundary, preventing the star from expanding endlessly. The balance is precise. If fusion produces too much energy, the star expands slightly, cooling the core and reducing the fusion rate. If fusion slows, gravity compresses the star, raising the temperature until fusion increases again. It is a natural feedback system that keeps the star stable for millions or billions of years depending on its mass. The mass of a star determines nearly everything about its life. A small star burns fuel slowly, lasting far longer than larger stars that blaze with intense luminosity and consume hydrogen rapidly. The Sun itself will spend roughly 10 billion years in this stable phase. More massive stars live shorter lives because their stronger gravity compresses their cores to higher temperatures, driving faster fusion. These stars shine brightly but burn out quickly on cosmic timescales. Once hydrogen in the core is depleted, equilibrium can no longer be maintained. The star begins to change, and gravity once again takes the lead in shaping its evolution. When hydrogen fusion ends, the core contracts under gravity, heating even further. For stars similar in mass to the Sun, this heating ignites helium fusion into carbon and oxygen. The outer layers of the star expand, forming a red giant. Gravity still holds the star together, but the balance becomes more complex as different layers burn different fuels at different rates. Eventually, helium fusion ends, and the core contracts once more. For stars not massive enough to fuse heavier elements, the collapse stops when electron degeneracy pressure becomes strong enough to resist further compression. This quantum mechanical effect, which has no classical counterpart, halts gravity and leaves behind a white dwarf. The star is dim, small, and extraordinarily dense, a surviving ember held up not by thermal pressure, but by the quantum properties of electrons. The Chandrasekhar limit tells us that if the mass of the remaining core exceeds roughly 1.4 times the mass of the Sun, electron degeneracy can no longer prevent collapse. The limit is not a guess, but a well-established threshold supported by the physics of dense matter. For stars more massive than this threshold, the collapse continues. As the core contracts, electrons are forced into protons, forming neutrons and releasing neutrinos. The core becomes a neutron star, an object so dense that a single teaspoon of its material would weigh billions of tons on Earth. The pressure resisting gravity now arises from neutron degeneracy, another quantum mechanical effect. But even this form of pressure has a limit. The Tolman-Oppenheimer-Volkoff limit defines the maximum mass a neutron star can have before gravity overwhelms even neutron degeneracy. If the core surpasses this limit, no known force can stop the collapse. Gravity takes complete control, driving the matter inward until spacetime itself curves so steeply that escape becomes impossible. A black hole forms, marking the end of the star's journey and the beginning of a new chapter in the story of gravity. Yet even in these violent transformations, the guiding role of gravity remains constant. It determines when fusion begins, how long it lasts, and how the star responds when fuel runs low. It shapes the size, temperature, and luminosity of every star. And when the star reaches its final moments, gravity dictates whether it becomes a white dwarf, a neutron star, or something even more extreme. The life of a star is therefore not a simple passage from birth to death, but a precise interplay of physical forces governed above all by the strength of gravity. As a star ages, gravity continues to negotiate with the changing conditions inside its core, guiding the transitions that follow the exhaustion of hydrogen. When hydrogen fusion ends, the core no longer produces enough outward pressure to counteract gravity. The outer layers, still full of hydrogen, respond to the shifting balance by expanding outward. As the core contracts and heats, the surrounding shell begins to fuse hydrogen once more, adding a new source of energy. This shell burning produces enormous luminosity, causing the star to swell into a red giant. The transformation seems slow on human timescales, yet it is rapid in the life of a star, driven entirely by the steady hand of gravity rearranging the internal structure as each source of pressure fades. Inside the contracting core, temperatures eventually rise high enough for helium fusion. In stars with masses similar to the Sun, this ignition begins suddenly in what astronomers call a helium flash, a rapid onset of fusion that stabilizes the core for another phase of equilibrium. The star shrinks somewhat from its most expanded size, but gravity still dominates the overall structure. The core now fuses helium into carbon and oxygen, while hydrogen continues to burn in a shell around it. Despite the layered complexity, the same principles govern every stage. Gravity compresses the core, fusion supplies outward pressure, and the star adjusts its size and temperature to maintain balance as long as fuel remains available. For stars several times more massive than the Sun, the story grows more intense. Their cores become hot enough not only to fuse helium, but to ignite successively heavier elements. Carbon fuses into neon, neon into oxygen, oxygen into silicon, and silicon into iron. Each stage produces energy that temporarily counteracts gravity, but the process accelerates as the star approaches the creation of iron. Iron fusion does not release energy. Instead, it consumes it. This marks an absolute barrier in the evolution of massive stars. Once the core fills with iron, no further fusion can provide the pressure needed to resist gravity's inward pull. The equilibrium that sustained the star for millions of years collapses in seconds. The sudden failure of fusion pressure leads to a catastrophic downfall. Gravity crushes the core so rapidly that electrons fuse with protons, creating a dense sphere of neutrons. The outer layers, no longer supported by the core, plunge inward until they rebound off the newly formed neutron-rich core. The result is a supernova, a moment of extraordinary brilliance that briefly rivals the light of entire galaxies. This explosion disperses heavy elements into space, seeding future stars and planets with the material from which they will form. It also leaves behind one of the universe's most extreme objects. If the remaining core mass is below the Tolman-Oppenheimer-Volkoff limit, gravity is halted by neutron degeneracy pressure, and a neutron star remains. These objects are astonishingly compact, spinning rapidly and emitting beams of radiation that sweep across the cosmos like cosmic lighthouses. If the core mass exceeds the limit, however, even neutron degeneracy cannot resist gravity. No known form of pressure can halt the collapse. The core contracts until it passes the point where an event horizon forms and the star becomes a black hole. This transformation is not speculation, but an outcome grounded firmly in the physics of dense matter and confirmed by the observation of compact objects throughout the universe. The path from molecular cloud to black hole or neutron star is mapped out by observable processes, each step supported by evidence gathered from supernova remnants, binary star systems, and the detailed spectra of stellar material. Gravity directs every stage, ensuring that mass and pressure determine the destiny of each star according to well-established physical laws. Even stars too small to trigger dramatic endings follow a similar narrative. When helium fusion ends in a low-mass star, no additional fuel can ignite. Gravity compresses the core until electron degeneracy pressure halts it, leaving a white dwarf. Over billions of years, this remnant cools slowly, fading into the cosmic background. Observations of white dwarfs across the Milky Way confirm their predicted sizes and densities, matching the theoretical equations that describe degenerate matter. The consistency between theory and observation reveals that even these quiet remnants obey the same gravitational principles that guide the most massive stars. Across all stellar lifetimes, the story is unified by one continuous theme. Gravity drives formation, regulates stable burning, triggers collapse, and determines every possible final state. It acts patiently, yet relentlessly, never improvising and never relaxing its hold. From the gentle contraction of a cold gas cloud to the fierce emergence of a neutron star, gravity remains the architect behind every stellar transformation. The night sky is not merely scattered with points of light, but with monuments to the long and intricate dialogue between pressure and pull, heat and collapse, birth and destruction. As we follow the life of a star toward its final moments, gravity becomes more than a guiding force. It becomes the decisive judge of the star's fate. Everything depends on how much mass remains in the core when fusion can no longer proceed. At this stage, the star has exhausted its nuclear fuel, and the outward push that once balanced gravity has faded. What happens next is determined entirely by the battle between gravity and the quantum mechanical pressures that arise from the behavior of densely packed particles. This final conflict is not theoretical conjecture. Its outcomes have been observed across the galaxy in the remnants of ancient stars, in the precise timing of pulsars, and in the chemical elements that fill interstellar clouds. For stars with masses similar to the Sun, the core eventually becomes a compact sphere of carbon and oxygen supported by electron degeneracy pressure. This quantum pressure does not come from heat or fusion, but from the inherent properties of electrons, which cannot occupy the same state. It is a kind of structural resistance that emerges even at low temperatures. Once the outer layers of the star have drifted away, the remaining core shines faintly as a white dwarf. Its radius, temperature, and density agree with predictions drawn from the physics of degenerate matter. Astronomers have measured these properties in thousands of white dwarfs, confirming that the balance between gravity and electron degeneracy pressure forms objects whose characteristics align closely with theoretical models. Over billions of years, these remnants cool and fade, but their structure remains stable, preserved by the quantum rules that halted their collapse. More massive stars face a different ending. When their cores collapse during a supernova, conditions become so extreme that electrons and protons combine into neutrons. The density rises to an astonishing level, and the core becomes a neutron star. These objects contain more mass than white dwarfs, but are far smaller, often no wider than a city. Neutron degeneracy pressure and the strong nuclear force hold them up against gravity. Observations of neutron star masses and radii derived from pulsar timing and gravitational wave measurements confirm that these exotic objects follow the expected physical laws. Their magnetic fields, rotations, and interactions in binary systems offer further confirmation. Neutron stars are not hypothetical. They are among the most precisely studied gravitational laboratories in the universe, but even neutron degeneracy has a limit. The Tolman-Oppenheimer-Volkoff limit, derived from the equations of stellar structure combined with principles of dense nuclear matter, sets an upper boundary on how much mass a neutron star can support. If the core left after a supernova exceeds this boundary, gravity overwhelms every known opposing force. In such cases, collapse does not stop. The core compresses past the point where even neutrons can resist. Space-time curves so steeply that an event horizon forms, marking the birth of a black hole. Observational evidence of stellar mass black holes in binary systems, along with the gravitational waves produced by their mergers, confirms that nature indeed follows this path when mass surpasses the threshold set by nuclear physics and relativity. This outcome is not speculative, but the only consistent interpretation of long-studied data. Even after a star's death, the influence of gravity continues through the material it leaves behind. Supernova explosions scatter heavy elements forged in the final stages of stellar life. These elements enrich the interstellar medium, becoming part of new stars, planets, and eventually living organisms. The oxygen we breathe, the calcium in our bones, and the iron in our blood all trace their origins to stars that lived and died under the governance of gravity. This connection is not poetic invention. It is an established scientific fact supported by spectroscopy, nucleosynthesis models, and studies of stellar remnants. Gravity does not merely shape stars. Through them, it shapes the chemical landscape of the universe. Thus, the life of a star becomes a testament to gravity's reach. From the earliest contraction of diffuse gas to the final collapse into a dense remnant, gravity never relinquishes control. It dictates the temperature, luminosity, and evolution of the star. It determines when equilibrium is lost and what new form will emerge. And through the remnants and scattered elements of stellar death, it influences the next generation of cosmic structures. Every point of light in the night sky is a living record of this long interplay between fusion and collapse, energy and curvature, creation and destruction. Before we enter the realm of black holes, pause for a moment and consider the weight of a question that challenges every intuition you have about space and time. What happens when gravity becomes so strong that not even light can find a path outward? If space-time itself can fold into a shape that traps everything within it, what does that say about the universe's hidden architecture? And if these objects truly exist, how do we study something that reveals its presence only through what it prevents us from seeing? Black holes first appeared not in observatories, but in equations. When Carl Schwarzschild examined Einstein's newly published field equations during the early years of the 20th century, he discovered an exact solution describing the space-time surrounding a perfectly spherical mass. This solution predicted that if enough mass were compressed into a small enough region, the curvature of space-time would grow so intense that nothing could escape. Einstein himself doubted that nature would ever create such an extreme object, yet the mathematics remained firm. It showed that gravity could carve a boundary in space-time known as the event horizon, a surface beyond which all paths led inward. Inside that boundary, the the curvature would increase without limit, indicating that the known laws of physics could no longer describe conditions there. This central region is called a singularity, not because it is a physical object with defined properties, but because it marks the point where current theory breaks down. For decades, black holes remained a mathematical curiosity. No telescope at the time could detect them directly, and many scientists believed they were too extreme to form from collapsing stars. Yet evidence began to accumulate when astronomers observed stars moving in ways that suggested the presence of massive unseen companions. In certain binary systems, one star orbited an invisible partner, while emitting X-rays produced by gas heated to extraordinary temperatures as it spiraled inward. The behavior of these systems matched the predictions for matter falling toward a compact object far heavier than any neutron star could be. The gravitational pull required to produce the observed motions allowed no other explanation. These findings did not rely on speculation. They arose from precise measurements of stellar velocities and radiation, grounded in well-documented data. At the heart of the Milky Way, astronomers found an even more compelling case. A cluster of stars near the galactic center followed tightly curved orbits around an unseen mass. Over many years of observation, their positions were tracked with increasing accuracy. The stars moved so rapidly and so close to the central object that only a supermassive black hole could account for the gravitational force involved. The mass was millions of times greater than the Sun, compressed into a region far smaller than the smallest volume in which any known form of matter could remain stable. General relativity provided a consistent description of these motions, and every measurement confirmed that gravity behaved exactly as Einstein's equations predicted near such an extreme object. Light itself becomes a tool for studying black holes. When material falls inward, it heats to temperatures so high that it emits radiation across the spectrum. The shape of this radiation, the speed of orbiting gas, and the pattern of light bending around the black hole all offer clues to the structure of the spacetime surrounding it. Gravitational lensing near black holes is not theoretical conjecture. It has been observed in multiple systems, revealing how light curves along paths shaped by intense gravitational fields. These signals show that black holes interact with their surroundings in ways entirely consistent with general relativity, leaving signatures that can be measured, analyzed, and confirmed. Jets of charged particles, launched from the regions around supermassive black holes, extend for thousands of light years. These jets do not arise from within the black hole, but from the complex interactions occurring in the swirling disk of infalling matter. Magnetic fields and rotation create the conditions for such jets to form, and observations indicate that these structures carry energy outward at nearly the speed of light. The presence of these jets in many galaxies, combined with detailed measurements of their properties, reinforces the understanding that black holes are central engines powering some of the brightest objects in the universe. What makes black holes particularly remarkable is that they represent both a triumph and a challenge for general relativity. On the one hand, the predictions of the theory match the evidence with extraordinary precision. The motion of stars, the radiation from accretion disks, and the behavior of light all follow the rules set by Einstein's equations. On the other hand, the singularity inside the event horizon marks a limit where those equations fail. This is not speculation, but a direct consequence of the mathematics. It signals that while general relativity describes gravity with exceptional accuracy across a vast range of conditions, it is incomplete in the most extreme regions. The breakdown at the singularity is a signpost pointing toward new physics, not yet discovered, that must eventually join with general relativity to form a deeper theory. Black holes, once doubted and dismissed, have become central to modern astrophysics. Their existence is supported by multiple lines of evidence, each independent and rigorously confirmed. They are no longer viewed as exotic possibilities, but as standard outcomes of stellar evolution and common residence in the centers of galaxies. They are the most extreme objects predicted by relativity and the most powerful indicators of gravity's ability to reshape space-time. The more astronomers searched for signs of black holes, the more the universe revealed their unmistakable fingerprints. One of the clearest paths to identifying them came from observing the behavior of matter as it approached the event horizon. When gas falls toward a massive object, gravity accelerates it to tremendous speeds. Friction within the swirling accretion disk heats the gas to temperatures so high that it emits X-rays and ultraviolet radiation. These signals can be measured with great precision, and their properties match what general relativity predicts for material spiraling around a black hole. The spectrum of the radiation, the timing of its fluctuations, and the motion of the inner disk all provide information about the mass and spin of the black hole. These measurements are not speculative. They come from decades of observations using space-based telescopes and ground-based instruments that continually refine the understanding of how matter behaves near extreme gravity. As instruments grew more sensitive, researchers began to study how time and light behave near these dense objects. According to general relativity, light leaving the vicinity of a black hole should lose energy, shifting to longer wavelengths. This gravitational redshift has been observed in multiple systems, providing yet another confirmation of the theory. In addition, the orbits of stars and gas close to the event horizon show distortions caused by the curved spacetime surrounding the black hole. When astronomers mapped the orbits of stars near the center of the Milky Way, they found that their speeds and trajectories aligned perfectly with predictions for a supermassive black hole. These stars act as test particles in a giant natural experiment, tracing the invisible geometry carved by gravity. Every measurement strengthens the conclusion that a massive, compact object sits at the galactic center, and no alternative consistent with known physics can explain the data. One of the most striking confirmations of black hole physics came from the Event Horizon Telescope, a global array of radio dishes acting together as a single instrument. By linking telescopes scattered across Earth, researchers achieved the resolving power needed to image the region immediately surrounding a black hole. The resulting picture of the supermassive black hole in the galaxy, called M87, showed a bright ring of emission encircling a dark central shadow. This shadow matches the silhouette expected from an event horizon blocking light from behind it. The shape, size, and brightness pattern of the ring agree with the predictions of general relativity for a rotating black hole. Years later, the image of the black hole at the center of the Milky Way offered a new test, one involving a different environment and a different mass. Both images confirmed that gravity behaves as Einstein's equations describe, even in conditions where spacetime is bent to extremes. Although black holes do not allow anything to escape from within the event horizon, they still influence their surroundings profoundly. Magnetic fields, rotation, and infalling matter create structures that extend far beyond the horizon. Some black holes launch jets of plasma that stretch across thousands of light years. Observations show that these jets carry enormous amounts of energy and affect the evolution of entire galaxies. Their structure and behavior reveal how matter and magnetic fields interact in the rapidly spinning spacetime near the black hole. The presence of these jets is not evidence of matter escaping from inside the event horizon, but rather a sign of how powerful gravitational and electromagnetic processes become in the regions just outside it. These features, observed in many galaxies, demonstrate that black holes are not isolated objects, but engines shaping the cosmic environment around them. Despite all these confirmations, black holes remain a source of profound scientific questions. The event horizon marks a boundary beyond which information cannot return to the outside universe, but what happens inside remains unknown. General relativity predicts that curvature increases without limit as matter approaches the singularity, but this prediction signals the breakdown of the theory itself. It does not describe what occurs at that point. Instead, it highlights the need for a deeper framework combining gravity with quantum mechanics. This need is not theoretical speculation, but a mathematical necessity arising from the equations. Black holes therefore stand at the intersection of what is known and what remains undiscovered. offering clues and challenges that guide the search for a more complete understanding of nature. Observations of black hole mergers through gravitational waves have added yet another layer of evidence. When two black holes spiral together and collide, they release energy in the form of ripples in spacetime. These ripples match the precise waveform predicted by general relativity for such events. The signals provide information about the mass, spin, and final state of the merged object. In each detection so far, the data align with the behavior expected from black hole physics. There is no need for additional assumptions or unverified theories. The universe itself provides the confirmation. Thus, the case for black holes is formed by multiple independent observations: stellar orbits, accretion disk radiation, gravitational lensing, direct imaging of event horizon shadows, and gravitational wave detections. All these lines of evidence converge on the same conclusion. Black holes are real. They behave exactly as general relativity predicts. They are not hypothetical. They are not conceptual boundaries. They are physical objects whose properties have been measured with increasing precision. They represent the most extreme triumph of Einstein's theory and the clearest signpost pointing toward the next frontier of physics. The existence of black holes, once a mathematical possibility, has now become a cornerstone of modern astrophysics. Yet their reality does not diminish the sense of wonder they evoke. If anything, it deepens it. Every observation that confirms their presence also highlights the limits of our understanding. For all that we can measure about the space-time surrounding a black hole, the interior remains hidden behind the event horizon, a region where current physical theories cannot provide clear answers. This boundary does not merely conceal information. It marks a threshold between the known and the unknowable, a place where gravity asserts itself with unmatched strength and challenges the frameworks that describe the universe elsewhere. One of the strongest demonstrations of a black hole's influence comes from the behavior of time itself. According to general relativity, time slows dramatically as one approaches the event horizon. This is not a matter of perception, but an objective effect arising from the curvature of spacetime. Light emitted near the horizon appears increasingly redshifted as it escapes, carrying the imprint of slowed time. Observations of matter spiraling inward confirm this effect. As gas nears the event horizon, its emissions stretch to longer wavelengths, consistent with the predictions of relativity. These signatures offer a glimpse into the extreme environment surrounding the horizon, revealing how the flow of time becomes distorted by gravity's intensity. Despite this wealth of information, the event horizon remains an absolute boundary. No signal escapes from within. The interior is inferred solely from equations, and those equations tell us that the singularity predicted by general relativity is not a physical object but a sign of the theory's breakdown. Space-time curvature grows without limit inside a black hole, indicating that the description offered by relativity cannot continue past that point. This is not a flaw, but a clue. It suggests that the structure of space-time must differ at scales or energies where quantum effects dominate. The pursuit of a theory that can describe these conditions is one of the central challenges in physics, motivated directly by the behavior of black holes. While the interior remains hidden, black holes reveal themselves in spectacular ways through their interactions with surrounding matter. Consider the regions where magnetic fields twist through rapidly rotating disks of gas. These fields channel material into narrow jets that shoot outward at nearly the speed of light. Observations of these jets show that they influence the structure and evolution of galaxies, regulating star formation and redistributing energy across vast distances. The power driving these jets originates not from the black hole interior, but from the intense rotation and magnetic forces near the event horizon. The processes involved are grounded in established physics, not speculative mechanisms, and their signatures appear consistently in galaxies across the universe. The detection of gravitational waves added a new way to study black holes. When two black holes merge, they create a final burst of gravitational radiation that carries information about the system's mass and spin. The shape of the waveform, rising in frequency and amplitude until the final ringdown, matches the predictions of general relativity with remarkable precision. These signals confirm that the merged object settles into a new black hole whose properties follow well-established equations governing rotating black holes. Each detection provides a clean test of relativity in the strong gravity regime. So far, every observation affirms that the theory holds, even under the most extreme conditions imaginable. These findings form a cohesive picture, supported by independent lines of evidence. The motions of stars near galactic centers reveal immense compact masses. The radiation from accretion disks shows the signature of material nearing an event horizon. The curved paths of light demonstrate how space-time bends around these objects. Direct imaging reveals the shadow cast by the event horizon itself. Gravitational waves confirm the dynamics of black hole mergers. None of these observations stand alone. Together they form an interlocking framework that verifies the existence and behavior of black holes in extraordinary detail. Black holes therefore serve two roles in modern science. They are powerful astrophysical objects that influence galaxies, regulate star formation, and generate enormous energy. At the same time, they are critical tools for probing the nature of gravity. Their extreme environments test general relativity in ways impossible to achieve elsewhere. They confirm the theory's predictions while highlighting the points where it must eventually give way to a more complete description of nature. As we leave the realm of black holes and continue through the story of gravity, the next chapter explores how the universe reveals these invisible giants not only through light and motion, but through the very fabric of space-time itself. The methods used to observe the unseen have grown more precise, allowing scientists to detect the faint whispers of distant collisions and trace the paths of matter around compact objects. These techniques do more than confirm theories. They open new windows into the workings of gravity, showing how much the universe still has to teach. Before we begin, consider a question that slips quietly through the universe itself. If gravity can shape the path of light, twist the flow of time, and send ripples across space-time, how do we observe something that does not emit light of its own? How do we study objects that hide behind horizons or clouds of gas or distances so vast that even starlight arrives changed by its journey? And if the universe speaks in more than one language, with light carrying one story and gravity carrying another, what new truths emerge when we learn to listen to both? The effort to observe black holes and other compact objects began long before anyone had the tools to see them directly. Early astronomers could only infer their presence from the motion of stars bound to unseen companions. A star orbiting an invisible partner reveals the mass of that partner through the shape and speed of its orbit. These measurements rely on well-understood physics. When a visible star wobbles in a predictable pattern, the mass pulling on it can be calculated from the motion alone. Systems where a bright star circles an unseen object, with a mass far greater than any white dwarf or neutron star, provide some of the clearest evidence for the existence of stellar mass black holes. The data do not require new theories or speculative interpretations. They follow directly from gravitational principles established and verified over centuries. Light also carries information about the conditions near compact objects. Gas falling toward a neutron star or black hole forms an accretion disk that heats to extraordinary temperatures. The radiation emitted from these disks spans a wide range of wavelengths, from optical light to X-rays. By analyzing this radiation, astronomers learn about the structure, temperature, and motion of the material. The way the spectrum shifts over time reveals how gas spirals inward, how magnetic fields influence the flow, and how gravity shapes the surrounding space-time. Observations of accretion disks have shown that matter near a black hole moves at high fractions of the speed of light, following paths predicted by general relativity. The timing of flares, the broadening of spectral lines, and the changing brightness of the disk all match the expected behavior of matter experiencing intense gravitational forces. As technology advanced, instruments were developed to explore these environments with increasing precision. Radio telescopes combine their signals to form arrays capable of detecting faint emissions from the centers of galaxies. Millimeter wave observations penetrated regions obscured by dust, allowing astronomers to observe gas orbiting close to supermassive black holes. The Event Horizon Telescope used this method to produce the first image of a black hole's shadow, revealing the bright ring of emissions surrounding the event horizon. Every part of the image, from the shape of the shadow to the distribution of brightness around it, agrees with the predictions of general relativity for a rotating black hole. This achievement required no speculative assumptions. It relied on the laws of physics verified through decades of experiment and observation. Motion itself becomes a tool for studying invisible structures in the universe. When matter or light passes near a massive object, its path curves along the shape of spacetime. This effect, known as gravitational lensing, can magnify distant galaxies, create repeated images, or stretch the light into arcs. These distortions are not artifacts of the instruments. They are real features of the universe and have been documented in countless observations. Gravitational lensing allows astronomers to map the distribution of mass in galaxy clusters, revealing not only the visible matter, but the dark matter that cannot be seen directly. This mapping relies on general relativity, which predicts precisely how spacetime bends in response to different mass distributions. By comparing the observed distortions with theoretical models, researchers confirm both the presence of dark matter and the accuracy of Einstein's theory. The most dramatic advance in observing the invisible came with the detection of gravitational waves. These faint ripples in spacetime arise when massive bodies orbit and collide, sending out energy that stretches and compresses space as it travels. For decades, gravitational waves remained a theoretical prediction because their effects were too small for available instruments to detect. This changed when laser-based observatories reached sensitivities capable of measuring variations in length far smaller than the width of an atomic nucleus. When two black holes merged billions of years ago, the waves they emitted traveled across the universe and eventually passed through Earth. The detectors recorded a signal whose shape matched the predictions for a black hole merger with remarkable clarity. This first detection in the year 2015 confirmed one of Einstein's final predictions and opened a new era of astronomy. Since then, dozens of gravitational wave signals have been detected, each carrying information about collisions involving black holes or neutron stars. These waves provide details about the masses, spins, and dynamics of the merging objects. In one case, the merger of two neutron stars produced both gravitational waves and electromagnetic radiation, allowing astronomers to observe the event in multiple ways. The combination of these signals revealed the formation of heavy elements, confirmed models of neutron star structure, and offered additional tests of relativity. For the first time, scientists observed the universe through both light and gravity, gaining insights unavailable through either channel alone. The ability to detect gravitational waves transforms the study of gravity. It allows scientists to observe events hidden from telescopes, including black hole mergers that emit no light. It provides direct evidence for the behavior of spacetime under conditions of extreme curvature. And it verifies yet again that general relativity accurately describes the dynamics of gravity, even in the strongest fields nature can produce. In the years following the first detection of gravitational waves, the universe began to reveal events that had remained silent for billions of years. Each recorded signal carried its own distinct story, a pattern rising and falling as two massive bodies spiraled toward one another. These waveforms were not random. Their shapes matched the precise mathematical curves predicted by general relativity. When two black holes orbit, they lose energy through gravitational radiation, drawing ever closer until they merge in a final burst that sends a sharp ripple across space-time. The signals captured by the detectors followed this pattern so closely that the masses and spins of the black holes could be determined directly from the shape of the wave. This agreement between prediction and observation offered a new confirmation of Einstein's theory, one that emerged not from starlight or orbital motion, but from the vibrations of space-time itself. As more detections accumulated, a larger picture began to form. The universe contains far more black hole binaries than astronomers once suspected. Many of these systems emit no light, making them invisible to telescopes. Yet through gravitational waves, they became clear parts of the cosmic population. These observations showed that black holes form in a variety of environments and that their masses range widely. Some are only a few times the mass of the Sun. Others reach dozens of solar masses. The distribution of these masses provides clues about the evolution of massive stars and the conditions required for black hole formation. Each detection therefore serves a dual purpose. It confirms the behavior of gravity in extreme conditions and contributes to the understanding of how the universe builds and shapes its most compact objects. The detection of gravitational waves from a neutron star merger extended these insights even further. Unlike black holes, neutron stars emit light when they collide. The gravitational wave signal was recorded first, followed by bursts of gamma rays and later by radiation across the spectrum. The combination of gravitational and electromagnetic observations created a detailed picture of the event. It revealed how the colliding stars produced heavy elements such as gold and platinum. It confirmed that neutron stars have internal structures consistent with models based on dense nuclear matter. It also provided another test of relativity. The arrival of light and gravitational waves from the same event showed that both traveled across the universe at the same speed, matching a key prediction of Einstein's theory and ruling out alternatives that proposed different propagation speeds for gravitational waves. While gravitational waves opened a new channel for observing the universe, other techniques continued to refine the study of black holes and compact objects. High-resolution spectroscopy allowed astronomers to measure the speed of gas orbiting near black holes with increasing precision. These measurements revealed that the gas follows paths shaped exactly as general relativity predicts. The inner regions of accretion disks rotate so rapidly that their light becomes stretched and skewed. The pattern of this distortion encodes information about the black hole's spin and the structure of the surrounding spacetime. Observations across many systems confirmed that these patterns remain consistent with theoretical models. Even the timing of small fluctuations in brightness caused by instabilities in the accretion flow match the expected behavior of matter near an event horizon. Radio observations deepened the picture further. By mapping jets launched from the regions near supermassive black holes, astronomers traced how magnetic fields guide particles for thousands of light years. These jets carry energy outward, influencing the growth and evolution of galaxies. The structure of the jets offers indirect but powerful information about the rotation of the black hole and the conditions in the surrounding disk. Observations show that rapidly spinning black holes can transfer energy from their rotation into the jets through well-understood physical processes. This phenomenon, confirmed repeatedly in many galaxies, demonstrates how gravity interacts with magnetic fields and matter to produce some of the most energetic events in the universe. Even quieter signals add to the evidence. Pulsars in binary systems act as precise clocks, their pulses arriving with consistent rhythm. When these objects orbit a companion, the arrival times shift slightly according to the curvature of space-time around them. This effect has been measured repeatedly and matches the predictions of general relativity with high precision. These observations do not produce dramatic images or powerful bursts of radiation. Instead, they reveal gravity's influence through the steady, dependable tick of a distant star. The fact that these small changes follow the equations of relativity so perfectly shows how deeply gravity shapes motion at every scale. Together, these diverse methods create a portrait of gravity that is both detailed and consistent. The universe provides countless opportunities to test Einstein's theory, from the faint bending of starlight to the violent collision of black holes. Each observation tests a different aspect of gravity. Each result fits within the same mathematical framework. No contradiction has emerged. Instead, the evidence continues to reinforce the view that spacetime itself responds to mass and energy in the ways described by general relativity. Yet these successes do not diminish the sense of mystery that surrounds the study of gravity. If anything, they sharpen it. The better scientists understand how gravity behaves in the observable universe, the clearer it becomes that the deepest questions lie in places still hidden. How does space-time behave at the smallest scales? What happens when matter is compressed beyond the limits known to physics? And how can a theory that works so well in the observable world fail so completely at singularities? These questions set the stage for the next chapter, where gravity meets quantum physics and reveals the limits of even its most successful descriptions. The invisible universe continued to open itself to observation as instruments reached sensitivities once unimaginable. With each signal, each refined measurement, and each sharpened image, the story of gravity grew clearer. Yet even as the data expanded, the underlying theme remained the same. The universe behaves exactly as general relativity predicts in every domain where it has been tested. From the slow drift of stars in long orbits to the violent mergers of dense remnants, the rules governing motion and light follow the same geometric framework. But observing these phenomena requires tools capable of capturing effects that are often faint, distant, and fleeting. The success of these tools marks one of the most significant achievements of modern science. One of the quiet but powerful confirmations of relativity comes from the long-term monitoring of stars near the centers of galaxies. In the heart of the Milky Way, astronomers have traced the orbits of stars with remarkable precision. These stars swoop close to the central black hole and then swing outward in elongated paths that repeat over many years. The curvature of their orbits reveals the structure of space-time near the supermassive object. The speeds they reach, the timing of their returns, and the angles of their motion match general relativity's predictions to a high degree. When one particular star passed especially close to the black hole, its light showed a gravitational redshift consistent with the slowing of time in strong gravitational fields. This observation offered another test, conducted in an environment far more extreme than anything on Earth, yet still following the same geometric laws. Observing compact objects also involves listening to the faint whispers of pulsars orbiting companions. These neutron stars emit precise pulses of radiation that function as natural clocks. When a pulsar orbits another star or another neutron star, the arrival time of its pulses shifts in ways determined by the curvature of space-time. Over years of monitoring, astronomers have measured these shifts with enough accuracy to detect effects such as the decay of the orbit due to gravitational wave emission. This decay aligns exactly with the predictions of relativistic models. The steady rhythm of these cosmic clocks therefore becomes another channel through which gravity reveals its influence. On larger scales, the bending of light by galaxy clusters provides a map of the universe's mass distribution. These clusters act as lenses, distorting the shapes of background galaxies. The details of these distortions reveal not only the presence of visible matter, but also the distribution of dark matter, which outweighs the luminous material by a significant margin. The patterns of lensing depend on the curvature of space-time created by all the mass in the cluster, and the results match models based on general relativity. These measurements do not require hypothetical forces or unverified systems. They rely on well-established physics and the precise observation of light across cosmic distances. Another line of evidence comes from timing the arrival of photons from distant sources. When light passes near a massive object, the travel time changes because space-time itself is curved. This effect, known as the Shapiro delay, has been measured in signals sent from spacecraft and in pulses from distant quasars. The observed delays match the predictions from Einstein's equations, adding yet another confirmation from a completely different domain. Even the way the universe expands on large scales relies on the geometric description of space-time. Observations of distant supernovae, cosmic microwave background patterns, and the distribution of galaxies all reflect a universe shaped by general relativity combined with the presence of dark energy. These results reveal not only the accuracy of the theory, but the richness of the universe it describes. But perhaps the most compelling aspect of observing the invisible comes from the way multiple methods converge on the same conclusions. Gravitational waves, accretion disk radiation, gravitational lensing, orbital dynamics, and pulsar timing all reveal features of the same underlying geometry. They test gravity in situations ranging from mild to extreme. They examine objects separated by vast distances and events spread across billions of years. And in every case, the results align. There is no competing theory that explains this wide range of phenomena with equal precision and consistency. Yet despite this triumph, observing the invisible universe also illuminates the limits of current understanding. While general relativity describes the curvature of spacetime with extraordinary accuracy, it does not explain the nature of dark matter or dark energy. It does not determine what happens at spacetime singularities or how gravity should behave when quantum effects dominate. These open questions are not signs of failure, but evidence that a complete theory must extend beyond the reach of what is currently known. Observations continue to guide this search by revealing where predictions hold firm and where they reach their limits. The invisible universe therefore stands as both a confirmation of Einstein's ideas and a frontier awaiting exploration. It shows how gravity shapes the cosmos, how light bends under its influence, and how matter responds when compressed to unimaginable densities. It also shows whether theory must eventually give way to something deeper. For now, the tools that observe the invisible form a bridge between what can be seen and what must be inferred, offering insights that guide the next steps of scientific discovery. Before we begin, consider a question that reaches into the very fabric of reality. If the universe is built from particles that obey quantum rules, and if spacetime itself bends and flows according to general relativity, how can these two descriptions coexist? What happens when matter becomes so dense and energy so high that both quantum uncertainty and gravitational curvature demand control of the same region? And if nature follows only one consistent set of laws, why do our two most successful theories refuse to merge into a single picture? The tension between gravity and quantum physics began long before scientists understood how deep it ran. Quantum mechanics emerged in the early 20th century to explain the behavior of atoms, electrons, and light. It revealed a world governed by probabilities, where particles behave like waves and where uncertainty is built into the structure of physical reality. General relativity, by contrast, describes gravity through the smooth geometry of space-time. It works flawlessly in regimes involving planets, stars, galaxies, and the large-scale structure of the cosmos. Each theory succeeded in its own domain, yet neither could replace the other. The universe clearly needed both descriptions, but their foundations were too different to blend. One of the clearest sources of conflict lies in the way each theory describes space and time. General relativity treats space-time as a smooth surface that curves continuously in response to energy and mass. This curvature determines how objects move, how time flows, and how gravity behaves. Quantum mechanics, however, describes fields and particles that exhibit fluctuations even in empty space. These fluctuations are not optional details, but fundamental features of quantum reality. When scientists attempt to apply quantum rules to the gravitational field itself, the mathematics breaks down. Instead of producing finite predictions, the equations generate infinities that cannot be removed by standard techniques. This failure is not due to a lack of imagination, but to a genuine incompatibility between the two frameworks. Another source of conflict appears when examining the smallest scales. Quantum physics suggests that particles cannot be localized precisely and that energy appears in discrete steps. Relativity, however, requires a smooth continuous geometry to describe curvature. When these views collide at extremely tiny distances, they produce contradictions. The very idea of a continuous spacetime becomes questionable when quantum fluctuations grow strong enough to distort the geometry itself. But no experiment has probed distances where these effects become dominant, leaving the true nature of spacetime at extremely small scales an open question. Black holes highlight this mismatch in a dramatic way. According to general relativity, the interior of a black hole contains a singularity where spacetime curvature grows without bound. This prediction signals that the theory cannot describe what happens under such extreme conditions. Quantum mechanics, which governs the behavior of matter at small scales, should become important in this regime. Yet quantum theory requires a fixed background spacetime in order to operate. Inside a black hole, spacetime is not fixed. It is dynamic and tautly curved. The two theories cannot be applied together without producing contradictions. The singularity is therefore not an object with known properties. It is a boundary where both theories reach their limits and where neither can offer a reliable description. Singularities also appear in the early universe. According to general relativity, the cosmos began in a state of extremely high density and temperature. But quantum mechanics must play a role at such scales. When researchers try to combine the two frameworks to describe these conditions, the equations become inconsistent. This signals that the physics of the early universe cannot be understood without a theory that unifies quantum rules with gravitational curvature. The need for such a theory is widely recognized, and many approaches have been studied. But no candidate theory has gained experimental verification, and none can yet claim to be the final answer. This is not a failure of the scientific method. It reflects the difficulty of probing energies far beyond what current experiments can reach. The problem extends into the behavior of vacuum itself. Quantum mechanics predicts that empty space is filled with fluctuating fields that contribute to the overall energy density. General relativity says that energy density curves spacetime. If one calculates the expected vacuum energy based on quantum principles, the predicted curvature of spacetime becomes enormous. Observations, however, show that spacetime is nowhere near that curved. The mismatch between these two predictions is known as the vacuum catastrophe, and it remains one of the largest unsolved discrepancies in physics. The fact that both theories work so well in their own domains, yet disagree so profoundly when combined, is a clue that a deeper framework is waiting to be discovered. Despite these conflicts, scientists do not lack confidence in either theory. Each has withstood countless tests and continues to predict physical behavior with extraordinary accuracy. The clash arises only in extreme situations. In everyday life, quantum mechanics describes atoms and molecules flawlessly, while general relativity governs gravity at the scales of planets and stars. The difficulty appears only when gravity becomes strong at extremely small distances, or when quantum effects become important in highly curved spacetime. These conditions are rare in the universe and difficult to reproduce experimentally. This rarity partly explains why a unified theory remains elusive. Still, the need for such a theory is undeniable. Without it, singularities remain unresolved, and the early universe remains only partially understood. The behavior of spacetime at the smallest scales remains unknown, and the mismatch between vacuum energy predictions and observed curvature signals a gap in current knowledge. These inconsistencies do not undermine the value of either theory. Rather, they point toward a frontier where both must eventually be replaced by something more complete. The clash between gravity and quantum physics becomes clearer when we look closely at how each theory treats the concept of measurement. In quantum mechanics, every observable quantity is defined through probabilities. A particle does not follow a single precise path. Instead, it exists in a range of possible states until a measurement forces it into one outcome. This probabilistic nature is not a sign of incomplete understanding, but a proven feature of the microscopic world. Countless experiments show that particles behave like waves, interfere with themselves, and exist in superpositions that collapse only when observed. These behaviors define quantum theory and cannot be removed without breaking its most successful predictions. General relativity, however, requires that events follow definite trajectories through spacetime. A planet orbits a star along a path determined by the curvature of spacetime. A beam of light bends in a predictable way when passing near a massive object. Even extreme phenomena, such as the inspiral of two black holes, follow precise mathematical curves that match observation with extraordinary accuracy. Relativity does not include probabilities in its description of motion. It describes a world where geometry and curvature determine a clear and continuous evolution. When scientists try to apply this geometric certainty to particles governed by uncertainty, the conceptual mismatch becomes unavoidable. Another fundamental difference lies in how the two theories define energy. In quantum mechanics, energy is quantized. Particles occupy discrete levels, and transitions occur in specific jumps. This quantization explains the structure of atoms, the emission of light in precise frequencies, and the stability of matter. General relativity, in contrast, treats energy as a continuous quantity distributed smoothly across spacetime. Curvature responds to the total energy density, not to individual quanta. When researchers attempt to use quantized energy levels to shape the smooth geometry of spacetime, the results conflict. The equations begin to produce infinities that cannot be removed without breaking the framework of one theory or the other. This is not a matter of adding corrections or adjusting parameters. It reflects a deeper incompatibility that cannot be patched from within either theory. These conflicts become most dramatic in regions where both quantum effects and strong gravity are unavoidable. Near the singularity inside a black hole, for example, matter is compressed to densities where quantum mechanics should dominate. Yet the curvature predicted by relativity becomes so extreme that spacetime itself breaks down. No known principle can describe the behavior of matter under such conditions. Similarly, in the earliest moments of the universe, when energy densities were extraordinarily high, quantum fluctuations and gravitational curvature must have interacted in ways that neither theory can describe alone. These situations serve as markers, pointing toward regions where a new unified framework must replace both general relativity and quantum mechanics. Even the structure of spacetime becomes uncertain when viewed through the lens of quantum theory. Quantum mechanics suggests that empty space contains fluctuating fields that constantly appear and vanish. These fluctuations are small at ordinary scales, but cannot be ignored at extremely tiny distances. If spacetime responds to energy, then these fluctuations should alter its curvature. But attempts to calculate this curvature produce values far greater than anything observed. The universe should curl in on itself almost instantly, yet it does not. This enormous discrepancy reveals another profound conflict between the theories. It is not a minor disagreement, but a gap many orders of magnitude wide. The fact that the universe behaves normally despite the predicted fluctuations suggests that something fundamental is missing from current models. Some attempts to address these conflicts involve modifying gravity at small scales. Others involve quantizing spacetime itself. Still others treat gravity not as a force or a geometric field, but as an emergent phenomenon arising from deeper principles. These ideas remain under active study, but none have been verified experimentally. Scientists are careful to distinguish between mathematical possibilities and physical reality. Without observational evidence, no approach can yet be considered correct. The lack of experimental guidance is part of the challenge. The energies required to probe these regimes directly are far beyond the reach of current technology. Observations of black holes and the early universe offer indirect clues, but the path to a complete theory remains uncertain. Despite the open questions, the conflict between gravity and quantum mechanics has led to important insights. It clarifies the limits of each theory and highlights the need for a unified description of nature. It also shows that progress in physics often arises not from the success of a theory, but from the points where it breaks. Just as the mismatch in Mercury's orbit pointed the way toward general relativity, the mismatch between quantum mechanics and gravity points toward a deeper framework yet to be discovered. The search for that framework is one of the central pursuits of modern physics, guided by the knowledge that both theories, though incomplete alone, capture essential truths about the universe. The tension between quantum physics and gravity becomes even more striking when we consider how each theory explains the flow of information. In quantum mechanics, information about a system is never destroyed. Even when particles interact, scatter, or transform, the underlying quantum state retains all information in some form. This principle is supported by experiments and by the mathematical structure of quantum theory. Yet when matter falls into a black hole, general relativity describes a world in which everything that crosses the event horizon is lost to the outside universe forever. The horizon allows nothing to escape, not even light. If a black hole evaporates through the process described by Hawking, the radiation carries no imprint of the matter that formed the hole. This appears to violate the quantum principle that information must be preserved, creating a conflict known as the information paradox. It is not a philosophical puzzle. It is a concrete contradiction between the predictions of two otherwise successful theories. The paradox exposes a deeper issue. Quantum mechanics describes events using fixed spacetime coordinates. The evolution of a system unfolds against a stable background. General relativity, however, makes spacetime dynamic. It curves, stretches, and evolves in response to matter. A quantum theory of gravity would need to accommodate a dynamic background, yet no existing framework fully succeeds in doing so. When researchers attempt to quantize the gravitational field in the same way they quantize electromagnetic or nuclear forces, the resulting equations produce uncontrollable infinities. Unlike other fields, gravity resists quantization through established methods. This failure suggests that gravity may not be a force in the same sense that other interactions are. Instead, it may emerge from deeper principles that quantum mechanics alone cannot describe. The early universe provides another arena where the clash becomes unavoidable. Observations show that the cosmos was once extremely hot and dense. At such scales, quantum fluctuations must have influenced the distribution of matter, seeding the formation of galaxies. Yet general relativity alone cannot explain these initial conditions. The equations point backward toward a singularity, a point of infinite density where the theory ceases to apply. Quantum mechanics should intervene long before densities reach such extremes, but without a unified framework, scientists cannot describe how the earliest moments unfolded. The universe itself contains clues to this hidden physics. Patterns in the cosmic microwave background reflect quantum fluctuations stretched across space-time. But interpreting these patterns fully requires a theory that blends the smooth geometry of relativity with the probabilistic nature of quantum physics. No such theory is confirmed. Experiments on Earth attempt to probe the boundary between the two realms, though the challenge is immense. Gravity is extraordinarily weak compared to other fundamental interactions. This weakness makes quantum effects in gravity difficult to detect. Even the smallest dust grains contain so many particles that their gravitational influence dwarfs any quantum behavior. Researchers attempt to study tiny masses in superposition states, hoping to detect hints of gravitational effects. These experiments push the limits of precision, yet no definitive signal has emerged. This absence does not imply that quantum gravity behaves in one way or another. It simply shows that current technology cannot yet reach the scales where the conflict would manifest directly. The mathematical differences between the theories reflect deeper conceptual divisions. In quantum mechanics, uncertainty is fundamental. Position and momentum cannot both be known exactly. Energy fluctuates even in empty space. In general relativity, by contrast, space-time has a structure that determines the motion of objects precisely. There is no uncertainty in the curvature or in the trajectories defined by it. Reconciling these two views requires either modifying the geometric foundations of gravity or redefining the quantum rules that govern matter. neither approach has produced a complete, experimentally verified theory. Attempts to quantize spacetime, to treat it as made of discrete units, face challenges in matching large-scale observations. Attempts to modify quantum mechanics to include gravity run into conflicts with established principles. Attempts to treat gravity as emergent from deeper systems remain unconfirmed. The lack of experimental evidence leaves all ideas provisional. Yet the conflict between the theories has shaped scientific progress in profound ways. It has led to new mathematical tools, new questions, and new lines of investigation. It has clarified where current theories succeed and where they fail. It has shown that gravity and quantum physics are not separate subjects, but interconnected aspects of a deeper system that remains partially hidden. Researchers look to black holes, the early universe, and hypothetical high-energy processes for clues. They examine the behavior of spacetime under extreme conditions, searching for signatures that signal the presence of quantum gravitational effects. But the path remains uncertain, and the answers remain incomplete. What is known is that the universe contains conditions where gravity and quantum physics must work together. Supermassive black holes at galactic centers, the tiny fluctuations that seeded cosmic structure, and the fundamental vacuum energy all point toward regimes where neither theory alone can describe reality. These regions serve as signposts, marking the boundary of current knowledge. They show that the world is governed by laws more unified than the theories we currently hold. But discovering those laws requires evidence that has not yet been found and a framework that has not yet emerged. As this chapter closes, the unresolved tension stands as one of the deepest mysteries in physics. General relativity and quantum mechanics both describe essential parts of nature with extraordinary precision, yet they cannot describe nature together. The universe obeys one set of laws, not two. Somewhere beyond the reach of current experiments lies a single consistent description. Finding it is not merely a goal for the future, but a necessity for understanding the universe at its most fundamental level. Before we step into the strange borderland where quantum physics brushes against the curved geometry of spacetime, let me ask you something. If nothing can escape a black hole once it crosses the event horizon, how can the universe allow such an object to lose energy? If a black hole appears perfectly dark from the outside, what hidden process could make it glow with a faint thermal whisper? And if the fabric of spacetime near the event horizon behaves differently from the world we know, what does that reveal about the limits of our understanding? The idea that black holes might emit radiation seemed impossible when it was first considered. General relativity states clearly that nothing escapes from within the event horizon. Light, matter, and any form of information remain trapped once they cross that boundary. Yet in 1974, Stephen Hawking performed a calculation that changed the way scientists think about black holes. By applying quantum field theory to curved spacetime, Hawking showed that black holes should emit a faint glow, a form of thermal radiation that carries energy away. This process, now known as Hawking radiation, does not contradict general relativity. It arises from the interplay between quantum fields and the geometry around the event horizon. Importantly, Hawking's result does not imply that anything crosses outward through the horizon. Instead, it shows that the vacuum itself behaves differently near such intense curvature. To understand why, we must step into the world of quantum fields. According to quantum mechanics, empty space is never truly empty. Fields fluctuate constantly, creating pairs of particles and antiparticles that appear and vanish in unimaginably short intervals. These fluctuations normally remain confined and leave no lasting effect. But near a black hole's event horizon, the curvature of spacetime alters the behavior of these pairs. When a pair forms very close to the horizon, one member may fall inward while the other escapes. The escaping particle becomes part of observable radiation, while its partner reduces the mass of the black hole by an equivalent amount. This mechanism does not rely on particles tunneling through the horizon. Instead, it emerges from the structure of quantum fields in strongly curved spacetime. Hawking's calculation revealed that the radiation has a temperature determined by the surface gravity of the black hole. Larger black holes emit radiation with lower temperatures, while small black holes emit more strongly. The temperature is exceedingly low for black holes formed from stars. A black hole with the mass of the Sun would have a temperature far below what any current instrument could detect. As a result, Hawking radiation remains a theoretical prediction, supported by extensive mathematical work, but not yet confirmed through direct observation. Despite this, it is widely accepted within the physics community because it arises from well-tested principles of quantum field theory and general relativity applied together in a regime where both are essential. One of the most striking consequences of Hawking radiation is that black holes are not eternal. As they emit radiation, they lose mass. This loss is incredibly slow for large black holes, occurring over timescales far longer than the current age of the universe. But for smaller black holes, the process accelerates as the mass decreases. Eventually, the black hole would evaporate completely, leaving no remnant. These predictions reflect the mathematical structure of Hawking's result and the known relationships between mass, surface gravity, and temperature. They remain consistent with all verified principles of physics, though the final stages of evaporation remain uncertain because they occur in a regime where quantum gravitational effects likely become important. Hawking's discovery also introduced a deeper puzzle. If black holes evaporate, what happens to the information carried by the matter that fell into them? Quantum mechanics insists that information cannot be destroyed. Yet if the final radiation emitted by a black hole is purely thermal, it carries no trace of the initial state. This contradiction forms the foundation of the black hole information paradox. It is important to note that the paradox does not indicate that Hawking radiation is incorrect. Instead, it reveals the limits of current theory. No existing framework can fully explain how information behaves in the presence of both quantum fields and strong gravitational curvature. The paradox is therefore a signpost pointing toward the need for a deeper understanding of quantum gravity. It remains an open problem, and no proposed resolution has been verified experimentally. Scientists have attempted to study phenomena similar to Hawking radiation in laboratory settings. Certain systems, such as flowing fluids and optical media, can create effective horizons where waves behave in ways analogous to those near a black hole. Experiments with these analog systems have produced signals that resemble Hawking's predictions. However, they do not directly prove the existence of Hawking radiation in astrophysical black holes. Instead, they show that the underlying mathematics applies to a wide range of physical systems, strengthening confidence in the theoretical result while highlighting the difficulty of observing it in nature. Hawking radiation stands as one of the most successful theoretical predictions connecting quantum physics to curved spacetime. It does not provide a complete theory of quantum gravity, nor does it resolve singularities or explain the underlying structure of spacetime at the smallest scales, but it does demonstrate that the quantum vacuum responds to gravity in fundamental ways, producing effects that cannot be captured by classical descriptions alone. It reveals that black holes are thermodynamic objects with temperatures and entropies, subject to laws that resemble the rules governing ordinary matter. These thermodynamic insights, supported by later work in quantum field theory and statistical mechanics, form one of the strongest bridges between gravity and quantum physics. The idea that a black hole possesses a temperature was already surprising, but Hawking's calculation also implied that black holes obey laws resembling those of thermodynamics. Decades earlier, before Hawking radiation had been derived, researchers studying the mathematics of black holes noticed that certain relationships echoed the classical laws of heat and energy. The surface area of a black hole's event horizon never decreased, mirroring the fact that entropy in a closed system never declines. The product of surface gravity and changes in mass resembled the relationship between temperature and energy. These parallels were purely mathematical at first, interesting but without clear physical meaning. Hawking radiation transformed them into physical truths. If black holes emit radiation with a specific temperature, then the analogy becomes a genuine thermodynamic identity, The event horizon area corresponds to entropy. The surface gravity corresponds to temperature. These relationships emerged not from guesswork, but from rigorous mathematics grounded in established physics. Still, the interpretation requires care. The entropy of a black hole is not associated with the matter inside the event horizon. Instead, it reflects the number of microscopic configurations that the horizon itself could possess, even though these configurations are not yet fully understood. The fact that the entropy scales with surface area rather than with volume suggests that information in gravitational systems might be stored differently than in ordinary matter. This insight has influenced many lines of research into quantum gravity, though none have yet reached experimental confirmation. It is important to emphasize that while the thermodynamic interpretation is mathematically consistent and widely accepted, it does not provide a complete picture of the microscopic structure of spacetime. Instead, it offers a clue that gravity and quantum mechanics must converge on a deeper set of principles not yet revealed. As scientists studied Hawking's result more carefully, they found that the radiation emitted by a black hole is remarkably featureless. It follows a thermal spectrum determined only by the black hole's mass, charge, and rotation. This absence of detail is central to the information paradox. When matter falls into a black hole, it carries complex information about its structure, yet the outgoing radiation carries only temperature-dependent energy. No known mechanism within current theory allows that information to escape. General relativity predicts that it remains hidden beyond the event horizon. Quantum mechanics predicts that information cannot be destroyed. Hawking radiation places these two principles in direct conflict. The paradox does not undermine the validity of either theory in their tested domains. Instead, it highlights the point where both theories must eventually give way to something more complete. Attempts to resolve the paradox rely on different ways of interpreting the connection between radiation and the black hole interior. Some proposals suggest that subtle correlations within the radiation could preserve information, though these ideas remain unverified. Others attempt to modify the behavior of spacetime near the horizon, but such changes must remain consistent with the confirmed predictions of general relativity. None of these proposals have gained experimental support. At present, the information paradox remains an open question. It demonstrates the limits of current theory without pointing definitively toward a solution. Researchers continue to explore these ideas because the paradox offers a rare opportunity to study where gravity and quantum mechanics intersect. Every detail of the problem arises from established physics. Nothing speculative is required to pose the question. Only the answer remains unknown. While Hawking radiation is far too faint to detect from astrophysical black holes, its consequences influence many areas of theoretical research. It reveals that the vacuum behaves differently in curved spacetime than it does in flat space. It shows that particle concepts depend on the observer's perspective. A stationary observer near a black hole perceives a thermal bath of radiation, while a freely falling observer experiences nothing unusual at the horizon. This difference arises because particle definitions in quantum field theory depend on how time is measured, and time flows differently for observers following different paths. These effects are not hypothetical. They reflect well-established aspects of quantum field theory applied to non-uniform gravitational fields. The study of Hawking radiation has also inspired experiments in analog gravity systems. In these laboratory setups, researchers create environments where waves encounter boundaries that mimic event horizons. For example, sound waves in flowing fluids can behave in ways that resemble the behavior of quantum fields near a black hole horizon. Light in optical media can encounter regions where its propagation speed changes rapidly, producing effects that parallel the mathematics of curved spacetime. These experiments have observed phenomena similar to Hawking radiation, though they do not constitute direct evidence for black hole evaporation. Instead, they confirm that the underlying physics of horizons and quantum fields produces consistent results across many different systems. This strengthens confidence in Hawking's calculation, while acknowledging the difficulty of observing the real process in nature. Even without direct detection, Hawking radiation occupies a central place in the study of gravity and quantum mechanics. It stands as the most thoroughly developed and widely accepted quantum effect associated with black holes. It demonstrates that horizons are not the perfectly silent boundaries once imagined, but regions where quantum processes reveal hidden aspects of spacetime. And although the full connections between entropy, information, and gravity remain incomplete, Hawking radiation continues to serve as a guidepost leading toward a deeper understanding of the universe. Hawking's insight did more than reveal a temperature for black holes. It reshaped the very way physicists think about horizons, information, and the structure of spacetime. Before his calculation, the event horizon was viewed as a silent geometric boundary, one that marked the limit of escape but carried no thermodynamic meaning. After Hawking radiation entered the picture, the horizon became a dynamic participant in physical processes. It possessed a temperature, an entropy, and a means of exchanging energy with the rest of the universe. These properties are not speculative additions. They follow directly from established quantum field theory applied to curved spacetime, using methods that have been tested in many other contexts. The surprise came not from the mathematics, but from the realization that black holes behave like thermodynamic objects, even though their interiors remain hidden behind the horizon. The entropy of a black hole, proportional to its surface area, raises questions that reach beyond the study of any individual object. In ordinary systems, entropy counts the number of microscopic states consistent with a given macroscopic description. For a gas, these states reflect the arrangements of its molecules. For a black hole, the underlying microstates are unknown. The fact that entropy scales with surface area rather than volume suggests that the information content of gravitational systems may be organized along boundaries rather than throughout regions. This idea has influenced many theoretical approaches, but it is crucial to emphasize that these approaches remain unverified. No experiment has confirmed any specific microscopic interpretation of black hole entropy. The established fact is simply that black holes possess entropy and temperature, and that these properties arise naturally from Hawking's calculations, combined with the earlier mathematical laws of black hole mechanics. Hawking radiation also connects black holes to the broader behavior of quantum fields in non-uniform gravitational environments. In flat spacetime, particle definitions rely on a stable notion of time. But near a horizon, the flow of time differs for observers following different paths. A stationary observer outside the black hole experiences a redshift that grows stronger as they approach the horizon. For such an observer, the vacuum appears filled with radiation. A freely falling observer, however, encounters no such effect while crossing the horizon. This difference arises not from contradictions in the theory, but from the observer-dependent nature of particle definitions in quantum field theory. The Hawking process reflects how quantum fields partition energy differently depending on the geometry of spacetime and the motion of the observer. This insight has been verified in many calculations involving accelerating frames and curved backgrounds, reinforcing the internal consistency of the quantum description. Even though the radiation predicted by Hawking is far too faint to observe from known astrophysical black holes, the lack of direct detection does not weaken the theoretical foundation. Large black holes have extremely low temperatures, colder than the cosmic microwave background. They absorb more energy from the universe than they emit, making the evaporation process effectively unnoticeable at present. Only black holes with masses far smaller than any known natural example would emit detectable levels of Hawking radiation. No such objects have been observed, and their existence is not required for Hawking's calculation to remain valid. The theoretical prediction concerns how quantum fields behave near a horizon, not whether specific black holes with particular masses exist. The relationship between Hawking radiation and black hole evaporation also deepens the information paradox. If the radiation is purely thermal, then the final state carries no record of the initial matter that formed the black hole. This leads to an apparent loss of information, contradicting the principles of quantum mechanics. The paradox remains unresolved, and no proposed solution has gained experimental support. It stands as a clearly defined problem arising entirely from established physics, signaling that current theories cannot yet describe the complete behavior of black holes. Some approaches attempt to identify correlations in the radiation. Others consider modifications to the structure of spacetime near the horizon, and still others explore the possibility that the paradox reflects a deeper principle not yet known. None of these ideas have moved beyond the speculative stage. The only confirmed facts are that Hawking radiation exists as a theoretical prediction, that it leads to evaporation over extremely long timescales, and that the question of how information behaves remains open. Analog gravity experiments provide further insight without directly addressing astrophysical black holes. In laboratory systems, researchers create horizons for waves in fluids, optical media, or atomic condensates. These horizons mimic some mathematical aspects of black hole event horizons, allowing scientists to explore how fluctuations behave in their presence. Several experiments have detected thermal spectra resembling Hawking radiation. While these results do not confirm the astrophysical process, they show that the core mathematical mechanism is robust and arises in many physical systems. This strengthens the theoretical framework, while maintaining the distinction between analog evidence and direct observation. Hawking radiation therefore occupies a special place in the study of gravity. It is not a complete theory of quantum gravity, nor does it describe the interior of black holes or the fundamental structure of spacetime. Instead, it marks the boundary where established quantum rules and general relativity overlap successfully. It shows that the vacuum interacts with curvature in ways impossible to capture with classical descriptions. It connects the behavior of fields, horizons, and thermodynamics into a single coherent picture, and it highlights the points where our theories fail, providing a roadmap for future investigation. As this chapter closes, the significance of Hawking radiation becomes clear. It is the most extensively studied and widely supported quantum effect associated with black holes. It is grounded in well-tested physics, even if it remains observationally elusive, and it points toward a deeper unity between gravity and quantum mechanics that has not yet been achieved. The unanswered questions it raises lead directly into the next part of the story, where gravity shapes not just individual objects, but the structure of the universe itself. From the moment the first galaxies formed in the early universe, gravity began weaving a structure so vast that no single observer could ever see it in full. Yet every piece of the sky, every filament of clustered galaxies, and every silent void stretching between them carries the imprint of gravity's architecture. The story begins with tiny fluctuations in the density of the early cosmos, barely perceptible variations recorded in the cosmic microwave background. These slight irregularities, shaped by pressure waves moving through the hot plasma, created the seeds of future structure. Gravity amplified these small differences over hundreds of millions of years. Regions with slightly more matter attracted additional material, while emptier regions grew emptier still. Slowly, the cosmic web emerged, forming a pattern of filaments and nodes, where galaxies gathered into clusters under the relentless pull of gravity. When astronomers studied individual galaxies, they found that gravity's influence extended beyond what visible matter alone could explain. Stars orbiting the outskirts of spiral galaxies moved with speeds that remained unexpectedly high, creating rotation curves that stayed flat rather than falling with distance. If only luminous matter contributed to the gravitational pull, the outer regions should have drifted apart. Instead, they remained tightly bound, revealing that an unseen form of mass was present. This invisible material, known as dark matter, formed extended halos around galaxies, dominating their gravitational structure. The evidence did not come from one observation, but from many. Galaxy rotation curves, gravitational lensing measurements, and the motions of stars and gas all pointed toward the same conclusion. Dark matter exists not as a speculative idea, but as the simplest explanation consistent with well-tested gravitational principles. Clusters of galaxies further strengthened this picture. When astronomers measured the speeds of galaxies within clusters, they found that far more mass was required to keep them bound than what could be seen in stars and gas. X-ray observations of hot intracluster gas revealed that the gravitational wells were deep, implying substantial unseen mass. Gravitational lensing provided even clearer evidence. When background galaxies appeared distorted by a cluster's gravity, the degree of bending revealed the mass distribution directly. These maps consistently showed that most of the mass was in dark matter halos, not in luminous material. The Bullet cluster, where two galaxy clusters collided, provided one of the most striking confirmations. The hot gas slowed and interacted during the collision, but the bulk of the mass, revealed through lensing, passed through with little resistance. This separation between visible gas and gravitational mass could not be reproduced by models without dark matter. On cosmological scales, dark matter played an essential role in forming galaxies and clusters. Simulations that include gravity acting on both visible matter and dark matter reproduce the observed cosmic web with remarkable accuracy. Filaments arise, clusters grow, and voids expand exactly as observations show. Without dark matter, the early fluctuations visible in the cosmic microwave background could not have grown into galaxies within the available cosmic time. Gravity shaped the universe not only through the matter we see, but through the vast reservoir of matter we do not. Dark energy adds a final layer to this cosmic structure. Observations of distant Type 1 supernovae revealed that the expansion of the universe is accelerating, a discovery confirmed through studies of galaxy clustering and the cosmic microwave background. While the nature of dark energy remains unknown, its effects fit cleanly within general relativity, appearing as a smooth component of energy that influences the dynamics of space-time on the largest scales. The geometry of the universe, the history of its expansion, and the distribution of galaxies across cosmic time all align with this picture. Gravity shapes the cosmic architecture, while dark energy shapes its long-term evolution. Across every scale, from the rotation of individual galaxies to the clustering of thousands of them and the expansion of the universe itself, gravity remains the guiding force. It reveals the presence of dark matter, shapes the formation of structure, bends the paths of distant light, and provides the mathematical framework through which the universe evolves. Much remains unknown about the unseen components of the cosmos, yet the gravitational story they tell is unmistakable. The universe is not a random scattering of galaxies, but a carefully sculpted structure, carved by gravity over billions of years into a vast and interconnected web whose patterns we are only beginning to understand. As we approach the limits of our understanding, gravity stands both as one of the most successful theories in science and as a gateway to questions that remain unanswered. General relativity has passed every test ever placed before it, describing the motion of planets, the behavior of clocks in Earth's gravitational field, the bending of starlight near massive objects, the orbits of stars around supermassive black holes, and the timing of gravitational waves from merging compact objects. Yet the very places where its predictions become extreme are the same places where the theory reaches its limits. At singularities inside black holes, curvature grows without bound, signaling that general relativity cannot describe conditions there. In the earliest moments of the universe, energy densities were so high that quantum effects and gravitational curvature must have acted together, yet no existing theory can fully explain those conditions. Quantum mechanics, meanwhile, governs the smallest scales of nature with unmatched accuracy. It describes atoms, molecules, and particles with precision beyond anything achieved by classical physics. But when quantum principles confront gravity, contradictions appear. Hawking radiation reveals that horizons are not silent, but thermally active. The information paradox shows that quantum principles and general relativity disagree about whether information can be lost. The vacuum catastrophe highlights a discrepancy between quantum predictions and observed spacetime curvature so large that no adjustment within current theory can bridge the gap. These tensions do not undermine the success of either theory in its own domain. Instead, they show that both are incomplete. Nature must follow a single set of laws, and somewhere beyond current knowledge lies a framework that unites quantum mechanics and gravity into one consistent description. Observational frontiers continue to push outward. Gravitational wave astronomy is still in its early years, yet it has already revealed mergers of black holes and neutron stars that were invisible to all other instruments. Each detection tests general relativity in strong fields. Each adds information about the behavior of matter under extreme conditions. The Event Horizon Telescope has imaged the regions near supermassive black holes, confirming the shape and size of their shadows. Future observations promise even sharper images and deeper tests of spacetime geometry. New telescopes will map the universe with unprecedented precision, tracing the distribution of dark matter and measuring the effects of dark energy across billions of years. Laboratory experiments continue to probe gravity at small scales, searching for subtle departures from known behavior. None have been found, but each result constrains the possibilities for new physics. In this way, the frontiers of gravity are defined not only by what is unknown, but by how sharply the known has been measured. We understand how gravity shapes stars, galaxies, clusters, and the universe as a whole. We understand the geometry of spacetime, where curvature is moderate or even extreme, as long as singularities are avoided. We understand how time slows near massive objects, how light bends, and how gravitational waves propagate. These achievements represent one of the greatest scientific successes of the modern era. Yet at the same time, the open questions, singularities, the nature of dark matter, the origin of dark energy, the unification of gravity with quantum mechanics, point toward physics not yet discovered. Gravity therefore stands as a force that is both precisely understood and deeply mysterious. It describes the motion of planets with exquisite accuracy, yet it hides the true nature of spacetime at its most extreme edges. It shapes the largest structures in the universe, yet it leaves unanswered the question of what composes most of the matter and energy in existence. It provides the mathematical elegance of curved spacetime, yet it fails exactly where quantum uncertainty begins to dominate. The journey through black holes, gravitational waves, stellar evolution, dark matter, and cosmic expansion reveals a universe governed by laws we understand well, but built upon foundations that remain partly hidden. And so, the story ends not with a final answer, but with a horizon of its own. Gravity has guided us from the falling of an apple to the bending of starlight, from Newton's equations to Einstein's geometry, from the life cycles of stars to the structure of the cosmos. It has revealed what is known with extraordinary clarity. It has revealed what is unknown with equal precision. The universe continues to expand, and so does our search for understanding. Somewhere beyond the limits of current theory lies the next chapter, waiting for the moment when observation and insight converge once again to illuminate the deepest workings of spacetime.